Okay, hello, everybody. Good morning. Okay, so yeah, let's start today's talk. I think in this morning we're going to have three talks, and the first talk is given by our local people, Vladimir Markovich, and the title of his talk is non-uniquely solving minimal surfaces. Okay, let's welcome.
This is better now, yeah. Right. So let's start with some definitions. We have a closed surface of genus G. This is going to be fixed throughout, and we also will have some number of hyperbolic surfaces of the same genus G, which I will denote by Mi, and we consider this product Riemannian manifold with the product hyperbolic metric. So useful here is that I can also use a blackboard if I need it. So please, that's handy. The input data is a map from this closed surface into the product, which is a diffeomorphism onto its image, which means that in each coordinate, it is a diffeomorphism. And then we have the product map. So this is kind of going to be a basic object here of interest. So just to reiterate, at the moment, sigma G does not carry a complex structure. It is just a smooth surface, or as you might think of it as a topological surface. So now we want to put a complex structure on it and consider the Teichmüller space of marked complex structures of genus on sigma G. And for each such complex structure, so if I replace sigma G with this S, I have this now a map from a Riemann surface into this Riemannian manifold into this product, and I can find a unique harmonic map. And in this case, this is with respect to the hyperbolic metric on the target, or the product hyperbolic metric, homotopic to my initial map G, which is kind of a topological data. And so as usual, as some of you might already certainly recognize, is that what you want to do here is to define the energy integral, or energy functional, which is simply computing the total energy of this harmonic map for any given complex structure. And this gives you a map, a function rather, on the Teichmüller space called the energy function. So why are we saying all this? Is because the critical points of this functional are called minimal surfaces. So the first and kind of the most basic interest of this talk is to talk about minimal surfaces of this nature in the product of other Riemann surfaces and this product manifold M. Okay, so this is what we want to talk about. So what is the first theorem? Well, this is this principle of Schoen and Yau, which says that it is kind of much more general than what we apply here. It's really a not hard theorem to prove, but almost always a first step in this sort of considerations. If you have a map of a surface into some other manifold which is essential, which means that the fundamental group of the surface is basically mapped injectively into the fundamental group of the target manifold, then that almost always means, and if the target manifold has some negative curvature features, that means that this energy function will be proper. And the significance of that is that therefore you can achieve its global maximum at least one point. So therefore we always have minimal surfaces in this situation. And this is the first observation, is that minimal surfaces do exist. Okay, so this is in fact not, I mean, that's of course been known for a long time, but, and it's not what we want to talk about in existence. We really want to talk about the uniqueness problem here. So let's immediately address this problem. So the theorem that I think was proved sometime in the 80s or early 90s, well, maybe Rick can tell us, is the theorem of Rick-Schoen. which is based on the work of Mikolev and Wolfson. And basically it says that if you have a product of two surfaces, then in fact, this global minimum that I just described to you is the unique minimal surface. In other words, the only critical point of this energy function. I'll tell you in a moment why that became significant in Higher-Teichmuller theorem. But nevertheless, this is a theorem that certainly, this theorem of Mikolev and Wolfson that was used by Schoen is certainly not an easy theorem to prove. It's kind of a significant result. So maybe to immediately give you the first consequence I derived from this was that same thing holds, but not just for the hyperbolic metric. In fact, you can take any conformal metric on this target Riemann surfaces M1 and M2. Schoen and Mikolev Wolfson, their proof really only works for hyperbolic metrics. But when I started working on this field, and you'll see the problem that really was of interest here, this was the first thing I could prove. And it was the first instance where I used the high energy harmonic maps. Basically, the idea was to transfer the first result into the second, show that they're equivalent, that it's enough to prove for one type of a conformal metrics that you have uniqueness, that it's equivalent, that the same choice for all of them. Okay, so this was this is one result, that you have uniqueness for any pair of conformal metrics. And then sometime after the original theorem of Schoen, Labrie conjectured that in fact this holds not just for a product of two Riemann surfaces, M1 and M2, but that, so I'll kind of put all this down here. You have always this product. So in this case, you can ask the question now, what happens with three surfaces and four and so on. And so the original theorem holds for two, that it's true when you have two, but the question was, Labrie conjectured in the 90s that the same is true for any number. And in fact, there was a reason he did this, because at this time, this theory, this so-called Higher-Teichmuller theory, began developing, where this product of Riemann surfaces M1 to M3 is basically a very special case of a lattice in a higher rank Lie group. So just so you know, the Lie group here is the product of PSL2Rs, and the lattice is, so this is the product of three PSL2Rs, so R3, and the lattice is the product of the corresponding Fuchsian groups. This is the simplest possible high rank lattice that you kind of pretty much can think of. And so what really Labrie wanted to generalize this question, not just for this very special case of Lie group, but he considered Lie groups and also representations in them. And well, the main examples, as people usually know, are when G is split and rho is Hitchin. So this is the so-called Hitchin component. And in the case when G is a Hermitian Lie group, then you assume that rho is Toledo maximal. So these conditions are, maybe you can just think of them some technical conditions guaranteeing they're replacing the condition that this map was a diffeomorphism in each component. This is that's what these assumptions that rho is Hitchin or Toledo maximal stand for. So as I said, when you have a product of two surfaces, this is the Lie group, underlying Lie group is the product of two copies of PSL2R, and lattice is the product of two Fuchsian groups. So again, kind of like as I described in this very special case, you can find this harmonic map into the corresponding symmetric space corresponding to this representation. And Again, then consider the energy functional. And again, for the same reason, for the assumption that rho is Hitchin or Toledo maximal, means that this map energy functional is proper. And it achieves its global minimum, and therefore you can conjecture or ask the question as to whether this functional has a unique stationary point, so unique minimal surface. So the reason that this conjecture was considered as a central problem in this field is because while harmonic maps and more generally this Hitchin correspondence, non-abelian Hodge correspondence gives you a so it gives you it parameterizes all these say good representations like maximal representations in Hermitian space. So you can parameterize them, but unlike the rank 1 case, this parameterization is not invariant under the mapping class group, and therefore it doesn't carry all the structure that you would want. So the idea here was to provide a different parameterization where instead of harmonic maps, you use this unique minimal map corresponding to each representation, and that this minimal map give you the parameterization, which would then be, by the uniqueness, would be mapping class group invariant. Roughly speaking, that was the reason. There certainly were others, but this was kind of perhaps the main point, as far as I understand it. And the first significant result were proved by Laborie, and then these other guys, the students of his, I believe, or some of them are. Right, so he proved, so he generalized Shane theorem for the product of two surfaces, which is this rank two group, Lie group of rank 2. He basically generalized to these good representations into all Lie groups of rank 2. And that was certainly a success. It's a very hard theorem to prove, I'd say, involved proof, but nevertheless, this gave hope that this conjecture might be true in this generality. So after all, you know, in Lie groups, the dichotomy usually goes, you have things that are true for rank 1, and then everything else, and then everything rank 2 and higher is like a different world. So you usually, at least coming from homogeneous dynamics and generally in geometry, these are the two cases that there are. So rank 1 on one side and higher rank on the other side. So here you already had proven something for rank 1, which is almost an obvious theorem here, and for rank 2. So it was certainly a good beginning and a hope. So what my interest was, I mean, I actually learned about this problem from my postdoc at the time, Chongling Li, and basically that got me interested in this problem, and I ended up disproving the Hermitian case of the conjecture, which is when the target Lie group is Hermitian. As I'll mention in a moment, this is really just equivalent to this case that I described here, because every Hermitian Lie group of a rank n contains a copy of product of n copies of PSL2R, I mean, product of them. So that kind of is the reason that it's enough to disprove it in this very nice situation here. So this is the statement of this result, is that you actually have more than, there certainly are maximal representations. In fact, for any Hermitian group, you can find these maximal representations which have multiple minimal surfaces. Let me say that while there is no unique minimal surface, I still think it's true that the number that all these minimal surfaces that exist are contained like in a compact part of the Teichner space. I mean, you can conjecture various things, but I would certainly conjecture this one to be true, and I strongly believe it's true, but it's kind of really hard to prove, it appears. But the theorem ought to be true. You can ask stronger questions whether there are finitely many of critical points and things like that, but I believe that this, just thinking heuristically here, if indeed you can prove that the set of critical points is compact, you simply might take like some sort of a barycenter of all these minimal surfaces and try to get a similar parameterization of this Hitching component using this barycenter, which should then be again mapping closed group invariant. I mean, this kind of idea exists, say, in theory of quasi-conformal maps, quasi-conformal groups. It was in that case pioneered by Tukia and Dennis Sullivan. So I'm imagining that something like that should work here as well. Providing that, but you certainly need to prove that the minimal surfaces, that these stationary points are in some kind of compact, but they must be in a compact set of the Teichner space. Then you have a chance. Anyway, well, I should say that in their most recent paper, which just appeared in the annals like last month, Nathaniel Sagman and Peter Smiley, they actually resolved this whole conjecture and proved this not just for the Hermitian space, which is technically easier than the split case, which is what they covered all Lie groups.
They produced counterexample?
Yes. So they proved the same theorem as this one, except that G is not a Hermitian, and you don't just assume that it's Hermitian. So yeah, and in fact, so Nathaniel was my student at the time, and Peter Smiley was my postdoc. So they worked together on this, and wrote this paper a few years ago. Okay, well, right. So as I said, it suffices to prove the theorem in the product of copies of PSL to R. Right. So this is just a restatement of this result, that there are multiple minimal surfaces, except that here you are now returning to this case here that we started discussing with. It's a kind of a simple case in some sense. So I'd like to tell you a few words about how to prove a theorem of this nature. So maybe a few other comments here. So, well, the use of harmonic maps in Teichner theory, I don't know who exactly was the first one to start, but typically Tromba, name of Tromba comes as one of the first people to actually have written something about it. And in fact, Tromba proved that the energy functional on the Teichner space is a polarity subharmonic function. This is generalizes the same or a similar theorem for the Hodge norm. So if on the Teichner space. But it's actually interesting. So this was sometime in the 80s. Tromba originally announced that the energy function is convex. That was the theorem that he wrote. But then it turned out that his proof didn't work for that. It only really showed that it's polarity subharmonic, which is a weaker statement. Still very good, but weaker. So one byproduct, and it has been an open problem whether energy functional is a convex with respect to the Weil-Petersen metric, which is what Tromba was originally claiming. So one byproduct of these constructions I carried out is that, in fact, the energy functional is not convex with respect to any Riemannian metric on the Teichner space. So this kind of side comment, but it settles this business once and for all. Okay, so now maybe to try to see how does one approach this problem. And of course, we want to keep in mind that the uniqueness holds when you have a product of two surfaces, and somehow it doesn't hold when you have product of more than two. So let's see how that in the end filters through. So this will be conceptual, and this is not how my original paper was written. I mean, but in the end, this kind of crystallized, the idea is crystallized, and now it's kind of clear what's going on. And this is, I'll tell you this end result, the clearer story. So you start with So if you don't know here maybe about harmonic maps and minimal, you might be disadvantaged, but I'm sorry about that. Nevertheless, some of you do, so hopefully you'll understand more. So we'll start with several with n, in this case, holomorphic quadratic differential on a fixed Riemann surface. And we will assume that they add up to 0. This condition will soon be explained. And so nevertheless, we will define 3 energy functional with respect to this data. So the data is just n holomorphic quadratic differentials. So we want to define 3 different functionals. One of them is the energy functional I told you about. But we want to relate it to some other ones that are easier to understand and better understood. This is kind of the idea. So let's start with this first, the first new linear functional is that whenever you have holomorphic quadratic differentials, they naturally yield the structure of R trees when you consider their horizontal and vertical trajectories, in this case, horizontal. And you always have this harmonic map. Well, you have induced action from the fundamental group onto the isometries of this tree. First of all, that's the equivariance condition. And then, so this tree is not a manifold, but it is sufficiently nice that you can also talk about harmonic maps into this somewhat singular space. And this is exactly what is done. So you construct, for each complex structure, you can now find a harmonic map into this tree. So this is all corresponding to some fixed n tuple of holomorphic quadratic differentials. Right. So I'll denote this one by rho. Rho is the representation of the fundamental group into this product, into the isometries of this tree. And the whole point of assuming that these holomorphic quadratic differentials add up to 0 is that S is now, because these are holomorphic quadratic differentials on the Riemann surface S, this condition means that S is critical point of the functional E rho. That is how you read this condition. So, well, this is a comment. By the way, it's not known that it's C2. This is some kind of open problem. It's just a side comment here. Maybe you can ignore it. But nevertheless, it's not clear exactly what's the smoothness of this. It's certainly C1 and probably not C2, but I don't know. Nevertheless, let's go to the second linear functional, to this, not linear, to the second functional on the Teichmüller space. This is where we now return to our original situation with the product of surfaces, but now we have to solve an equation, and we find these harmonic maps from the Riemann surface S into certain Riemann surfaces M, J, T by solving, by finding harmonic maps whose Hopf differential is equal to Hopf differential of these maps is equal to T phi I. You should think of T as being a very large number here. And as long as it's fixed, you can solve this equation. This is that you can solve this equation is a result of various people. Actually, Hitchin was the first one to show that you can recover a harmonic map from its Hopf differential, or more generally, in general Lie group case, you can do it by if you have a prescribed Higgs field. But in this very simple case, the Higgs field is just a holomorphic quadratic differential. Also, this was proved by Tom Wan and also Mike Wolf in the 80s. These are old theorems. Okay, so, and then we have the second energy functional is that as long as you fix T, you have a map into the product. These holomorphic quadratic differentials don't just define the harmonic maps, they define the target Riemann surfaces. That is also true. So, but nevertheless, by some procedure, you define this new linear functional. For each T, it just corresponds to this case we began with. So maybe we'll keep track of these functionals. We had E rho, which was corresponding to R3s. And then we have E T rho, which corresponds to the product of MT, well, the manifold MT, which is the product of these Riemann surfaces. And again, S is a critical point of this second functional as well for the same reason, that these guys add up to 0. So that's what it means that the minimal map, if you have a harmonic map on a surface, the map is minimal if and only if its Hopf differential is 0. And if you have a map into a product, Hopf differential is the sum of the Hopf differentials in each coordinate. That's why the condition becomes so simple. So the first equivalence theorem that can be proved and that we proved is that if Riemann surface is not a local minimum of E rho, I mean, no, well, it's not just if, I mean, it's if and only if, and in fact, that's important. So it is not a local minimum for E rho if and only if it is not local minimum for this one when T is large enough. So what this heuristically means is that this linear functional, well, this functional approaches this one when T is large. This is kind of the idea, is that you get these equations kind of decouple, as they call in this field, and simplify. And these harmonic maps, which are solving a nonlinear second order elliptic equation, converge to something much simpler, to a much kind of more prosaic map that you can understand directly, which is this product into R3. But the connection is more deep than that. It's not just some obvious convergence. It actually, you can show that being a local minimum becomes equivalent, and that's kind of a pretty strong statement. And this will help us. So we want to really, in the end, understand this case, but it's much easier to understand this, the first case. And this is a equivalence theorem is kind of moving the problem from here to here. And so we can observe that, so by Schoener's result, the only critical points of the second functional here for every T, simply because the product, you have only two things in the product, then you also know that this linear functional here now automatically has a unique critical point. And so in fact, Wentworth observed this some 15 years ago or something, that this gives a new proof of Mazur's theorem, which says that if I give you a pair of measure eliminations with certain properties that are basically transverse to each other, then you can find a unique Riemann surface on which these pair of measure eliminations are realized as a vertical and horizontal foliation of that quadratic differential. So the uniqueness part of that Mazur theorem, well, and also is basically, can be now, through this equivalence, could be simply seen as the, comes from this chain theorem, from harmonic maps. So you prove a statement purely in Teichmüller theory by using a statement about the uniqueness of minimal surfaces. And this is not the only instance. I mean, I have proved many other statements, things like Reichs-Trebel inequalities and so forth, can all be deduced from this chain result when you apply it to high energy harmonic maps. Okay, so let me describe you the third differential, the third functional. So this is the first, the second. And again, remember our input are these n quadratic differentials that add up to 0 on a fixed Riemann surface S. And for now, I will assume that they are squares, that they are actually squares of a billion differentials. You can certainly find such examples. And now we're gonna take, because you have a billion differentials, but taking their real part, you get elements of the first cohomology class, and taking simply the real part of these billion differentials. And that gives you the Hodge norm, which is simply the energy of the corresponding harmonic map from the universal cover of the Riemann surface into the real line. Or in a special case, from the Riemann surface onto the unit circle, if the form is, if the one form is given over Q. I mean, those are dense, so you can actually even think about this case. So this is the Hodge functional I'm telling you about. you simply take the sum of the Hodge norms of each of them. So the Hodge norm is just also an energy. It's energy of a harmonic map from a Riemann surface onto the circle, or more generally from its universal cover onto the real line, which on the level of the fundamental group gives you the corresponding representation. So again, S is the critical point of this Hodge functional. So by this data, we have now these three E chi. We have these three functionals. And I already told you that for high energy harmonic maps into the product of Riemann surfaces, not being a local minimum here is equivalent between the first two. And the second equivalence theorem is basically establishing the connection between the first and the third functional. And it's telling you that if you're not a local minimum for the first one, then you are not a local minimum for the third one. To go backwards, it's kind of similar, and for all intents and purposes the same, but you have to assume that if you are unstable point, if S is unstable point for here, then it is unstable here. There is a little difference. I mean, not being a local minimum, being unstable is a kind of a weaker condition than saying not being a local minimum. That's a little subtlety. But we are really interested in the stability condition. So this will suffice this second equivalence theorem. So kind of the first order approximation is that these two results are making connections between being unstable point for these three different functionals on the Teichmüller space. And only one, and we are now interested in the second one, but can get a better handle on the first and third. So let's see what that really amounts to. So the point that can be derived here is that if you start with the Hodge functional, which is certainly a natural and nice thing, and if you are unstable for that, then you are going to be unstable for this harmonic, coming from this harmonic map into products for every high enough T. Okay. This is so unstable here gives you examples of unstable here. And therefore, so if we want to prove this main result, we need to really show and find n tuple of one forms so that these Hodge norms, that the Hodge norm is unstable, that it has critical points of this Hodge norm functional which are not stable. That is what's required here. And now, then this makes a connection with the classical theory of minimal surfaces, because when n is equal to 3, every non-planar minimal surface, equivariant minimal surface in our triply periodic, as they call it in this field, triply periodic minimal surface is unstable. So that provides you with plentiful examples of these Hodge norms, because by this Weierstrass representation, you can recover from this minimal surface in the 3 torus, you can find, simply by restricting to the coordinate functions, you get 3 harmonic maps from the surface onto the 3 circles that give you this torus. And then you take alphas to be the corresponding one forms, the DZ operation applied to the harmonic map. So therefore, you easily and naturally produce these examples. They are very plentiful. And all of a sudden, you solve this theorem. So I should, maybe this was mentioned in the other day. There are many such examples. So Schwartz P surfaces of genus 3, in fact, you can find these minimal things of genus 3 that are going to be certainly unstable, and they can be used. Maybe we pause here and say, why is the Schoen theorem true and we still have this? Is because this function, the Hodge norm of only sum of 2, is not going to have unstable points. That would be the reason. So, because if you have a minimal surface in the plane, doubly periodic minimal surface, then it's going to be stable. Okay, so here the catch is that it's non-planar. You need a non-planar minimal surface in a higher dimensional torus of dimension at least 3. And that is really how the thing breaks down. Okay, so this now basically by these equivalence results means that this function for high enough, for large enough t, we produce examples with many critical points, with non-stable critical points. And therefore, because we have one global minimum, we must have more than one critical point. That would be the conclusion. And in the end, after careful analysis, it all really comes from these examples of triply periodic minimal surfaces in R3. So maybe this last part, I'll tell you about, well, also, so something a little bit more classical. It's more how these techniques and ideas used here can inform our knowledge about some more classical problems. In other words, you can think of the problem here is that, and what I want to explain. So if you have a Jordan curve, you of course can find a minimal disk bounding the Jordan curve, but this minimal disk may not be unique and in fact may not be stable. And it's a question whether we can say something about when it is going to be stable. Can we give some analytical condition? And how does this previous discussion, what are the ramifications here? Of course, I don't know if if people are interested when they are stable, but at least this is some kind of derivative result. And the reason I wanted to include it here is because people might know about this even if they're not really interested or know more generally about minimal surfaces, and second, or higher Teichmuller theory. And second of all, the criterion for non-stability of minimal disks that we found provides new proofs of some classical theorems, like about the N-per surface that I will tell you in a moment. So again, this is the minimal disk is harmonic in each coordinate, and the corresponding Hopf differentials of each coordinate maps add up to 0. So that's analytical condition that it's minimal. And then you have the corresponding one forms. So these phi i's are squares of alphas. So that's the connection. So phi I is alpha I squared. So this is called the Weierstrass N-per datum. And as I said, every curve bounds in R3 bounds a minimal disk. That's a Radot-Douglas result, of course, from almost 100 years ago. But these disks are not unique. A nice example is this actually minimal, the N-per surface is actually an entire minimal surface. It's over the entire plane in R3. Well, it's given by these equations, which I'm not going to discuss. That's just what it is. And but what you can do is that because this is a surface given over the entire plane, you can restrict onto a disk of radius r, and then when you intersect the surface with a cylinder above this disk, you get a minimal disk, which is of interest here. So right, and then the question is whether this disk is stable, unstable, and so forth. And the classical result says that this disk is unique and actually stable if and only if the radius is 1. When r is equal to 1, that is a kind of a transitional case. And when r is bigger than 1, this disk is not stable. Okay. So this is a picture of the N-per surface. As you can see, the surface gets very complicated. And you can imagine that when r is bigger, you have more room for maneuver. Of course, just by rights, by first principles, when r is very small, the surface will clearly be stable and unique because locally because it's smooth, so it's just going to be a plane. But as you kind of expand, you run into trouble and become unstable. This is a little technical condition which you might ignore. Some of you in the audience might have seen this before. It's called the Alfors-Berling or just Berling transformation. It's of course singular operator. In real analysis, this is a version of the Riesz transformation. In complex analysis, it's called Berling transformation. Anyway, this Berling transformation plays actually a very important role in all of these discussions, although in the end, it doesn't really feature in the last proofs, but it enables you to characterize when a minimal disk is unique. It's stable, I'm sorry. So like when this minimal disk is stable, you can give an analytical condition involving this singular operator called the Berling transformation. And well, this is a condition I'm not going to, of course, discuss it. But I can certainly tell you that it has consequences, and that consequence is that this gives you a condition as to when a minimal disk is stable. And it's in fact if and only if, in terms of this, in terms of the Berling transform. Alfors called this Berling transform, he called it the Hilbert transform in his book. Some of you might know it under that name. Well, again, what this does and what is the use of it is that you start with Weierstrass and Epper data of the minimal disk, and you plug it into this equation, into this inequality, and check whether it's satisfied, and that is going to compute whether your minimal disk is stable or not. When the Epper data are polynomial, which is of course geared up towards the case if you have minimal surfaces that are entire, given over an entire plane, this criterion becomes kind of more something you can compute. You can't really compute without some serious computation using computer this Berling transform, but with polynomials, you get this special case, and which again I'm not describing. But anyway, when so this also enables you to approximate the general situation with polynomials. So at any rate, there is it's not just a criterion abstract. It's something you can apply and compute and check whether your minimal disk is stable or not. The consequence is that so here this page describes how to apply this criterion to the Epper surface, and it really checks and verifies that Epper surface is unstable when R is bigger than 1 or radii bigger than 1. So it is a this kind of attests this method, and it's pretty precise here. So this criterion makes sense. And well, I mean, this is an old this discussion about the Epper surface is like 100 years old. I'd imagine, maybe even more. But now you have a kind of some maybe more streamlined method of checking these things, should you want to do that. And so this is actually a minimal disk that I constructed before knowing much about minimal surfaces. This was how, in my original work, when I disproved this conjecture about this Labouric conjecture in this product case, my proof was based on the non-stability of this particular minimal disk in R3. I actually was not aware that people knew of that actually such disks exist. So I constructed one myself anyway, and then my student Nathaniel drew the picture of that minimal disk. So this is a little picture. So you have the Epper surface, and then you have this one, just kind of for fun. But it tells you that to be unstable, you have to kind of have a lot of curving around, and that kind of destabilizes the minimal disk. And I think I'm right on time. So thank you for your attention.
Yeah. So are there any questions?
Yeah. Thank you for your talk. I'm not an expert, but I want to ask a question from perspective of statistical mechanics. So is it possible to consider Gibbs measure, like e to the minus beta energy functional acting on these surfaces, and then consider beta going to infinity and study ground states like that? Because sometimes the limit of these Gibbs measures kind of chooses particular ground states, and or it is a unique limit of this and give you some probability distribution of existing ground states.
Okay, so the principle you're describing, the principles here in the end, and more generally, in fact, I'm now writing something involving this in this kind of non-abelian Hodge correspondence and in Riemann-Hilbert correspondence. You have these principles that when the energy is large, then the equations, either the giving the ODs, giving the Riemann-Hilbert correspondence, or the Hitchin equations, they kind of decouple and become much simpler in the limit. And it is essentially, this is a really a simple version of this, what happens here. So this originated from physics. I'm not exactly sure whether it originates from this example. I would imagine yes. I simply don't know enough about these things. But the people who brought this into this field of symmetric spaces, minimal surfaces, were people essentially from physics. Yeah, so I'd imagine that. So I'm concretely referring to something called the WKB analysis. So this is something that can be carried out in this context, and this is a version of this. That's a simpler version of this, but it is a version of that. But I'm not sure whether it's exactly how it's related to these Gibbs states.
Yeah, well, we can talk about it.
Yeah.
You mentioned about uniqueness.
Yes.
In general field that you know which tool you need, given a Jordan curve. I did one work with units 50 years ago, but I don't know whether there's any more progress. So we proved that for Jordan curve with total curvature in RT less than 4, let's say you were 4 pi, then there's only one minimal piece. Actually, no high genius minimal surface, except the unique minimal piece. That's a general field.
Yes.
I don't know whether
I should have mentioned this. I mean, I am actually aware of this result. And what Yao is saying is, you can see in this picture, like what he's saying, if the curvature of the curve that bounds the disk is not too big, then it's minimal. And in these examples, when you are non-minimal, you have a lot of curving around. So that would be, but I don't know. So these are results. So we do give a criterion, in fact, equivalence as to when you're stable. Uniqueness is much harder entirely, to be honest, because that's a global thing and stability is a local. So we were able to really characterize stability. But I don't know about the other results of the uniqueness. I don't know I don't know of any other result like this. This is the only, for me too, yeah. That's the only result I know too, yeah.
Okay, yeah, because
there's a possibility for 5 genius minimal surface.
To exist, yeah, okay. Yeah.
So this should be interesting.
yeah, okay, yeah, because of time, probably we'll ask one more question. Yeah, Rick.
Okay, Rick and Nikolai. Rick, yeah.
Yeah, thank you for the really interesting talk. So, can you just briefly say what new ingredients are needed for the Sagman-Smiley result? Do they also reduce? They don't reduce to the same setting of products, or?
Well, yeah, all of this has to be reinterpreted there. This is kind of the first main object, difficulty and obstacle. So it's cumbersome, and they need to understand. So instead of these R trees, now you have to talk about buildings, which are these boundaries of Lie groups, and some harmonic maps into buildings. That's already that's motivated by trees, but it carries more difficulty.
I see.
For example, that's one thing. Then this Hodge norm, all these things have some new meaning. And this high energy analysis that I use, this idea still of course works, but you need more than that. So instead of these estimates that I used, which are not, which are kind of suited for this simple situation, they use this more general result of Mochizuki, but it does the same thing to understand this decoupling in high energy harmonic maps. So these are the two, perhaps I would say, the two main obstacles, but quite demanding things, quite difficult to carry out. And I should say, even when I disproved this conjecture a couple of years ago, people believe that it's still true in the split case, in the PSL-NR case. So there was a
surprise.
It was still surprising what they did. Yeah.
Okay, thank you.
Okay, so yeah, it's thanks to Marquisha again. Okay. Thanks.
I like that.
Okay, so let's start our second talk. The second talk is given by also our local people, Akito Futake, and the title of his talk is on the 姚田 Donaldson conjecture concerning canonical calorimetrics. Okay, let's welcome.
Thank you very much. I'd like to talk about Yao-Tian-Donaldson conjecture concerning canonical calorimetrics. So in Kähler geometry, there have been studies to prove the existence of kind of special metrics is equivalent to a kind of K stability or K polystability condition. The special metrics are typically Kähler-Einstein metrics, constant scalar curvature metrics, or extremal metrics. Extremal metrics include CSCK metrics, Kähler-Einstein metrics, as a special case, and Kähler-Ricci solitons, Sasaki-Einstein metrics, and many more other. And Kähler-Ricci soliton is an extension of Kähler-Einstein metric. Sasaki-Einstein metric also include Kähler-Einstein metric as a special case. And so weighted CSCK metrics is a rather new notion, includes all the above examples. I briefly explain the idea. XG is a compact Kähler manifold of complex dimension n. And suppose we have a Hamiltonian torus action for the respect to the Kähler form regarding the symplectic form. And I denote by delta the image of this moment map and the compact complex polytope. And SG, the scalar curvature. And we choose VW positive functions on delta, and weighted scalar curvature is defined by this complicated formula, but just so introducing this V and W, particular choice of V and W, we get the old example I listed above, like this. And weighted extremal Kähler metric is a metric for which the gradient of the weighted scalar curvature is a holomorphic vector field. This is equivalent to say that SVW is a composition of some affine function L on delta with the moment map. This equivalent. and VW is equal to 1. In this case, these vanish, this 1, and this, so just SDW is exactly the scalar curvature, and this is the Calabi's extremal scalar metric. And if L is constant, then it is a CSCK metric. And if first term class is positive, so X is Fano, and Kähler form belongs to this first term class, then it is a positive Fano Kähler-Einstein metric. And so, as I said, various choices V and W, L gives a various canonical Kähler metric listed above. And in 1977, Professor Yao proved the Calabi conjecture on the Kähler-Einstein metrics. So if first term class is negative, there's a unique Kähler-Einstein metric in the 1. And first term class 0 case, there is a unique Kähler-Einstein metric in each Kähler class. Almost 50 years later, last year, there's an announcement on the archive that there's some answer to this YTD problem. Let XL be a polarized manifold. This means that L is a holomorphic line bundle with first term class positive. So, and this class is regarded as a Kähler class. And assuming V concave, let S be a compact Lie group, including the torus, Hamiltonian torus action, and S is between T and AutoXL. AutoXL is the automorphism of X, lifting to the action on F. Then the following equivalent. There is S invariant weighted extremal Kähler metric in the first chunk of L. So just ignore all this, just weighted extremal metric, and XL S equivalent relatively weighted K hat polystable. Just think of this as some modification of K stability, K polystability. And XL is a uniformly S equivalently relatively weighted K hat polystable. Just think of this, some notion called uniform stability. This talk will review 50 years of development between Yao and Luxon-Johnson. And the important part of Luxon-Johnson's work is the CSCK case. This is a new result already. And the weighted case is just modification of this CSCK case. So I'll mainly talk about this CSCK case. And also I mainly follow recent work on uniform stability. So let's review basic definitions. Test configuration and case stability I review. Let XL be a polarized manifold. An ample test configuration with XL, Cal L. I simply call XL for this Roman XL consists of the following. A flat C-star equivalent projective morphism of normal schemes from chi to X to P1, and C-star equivalently ample. This is important keyword here at this talk. A Q line bundle over Lx and Xt are all isomorphic except for T non-zero. So at 0 in P1, we don't know what it is, but outside 0, they are all isomorphic to the given polarized manifold. And but there is a C-star action on XL. So so like T, small t belongs to C-star, and T approaches 0, it goes to something unknown, even singular variety. So this just describes sort of C-star equivalent degeneration of XL to some singular ones. This is what I just want to describe. Donaldson-Stark invariant, so it's my name, is defined by this formula. There's other descriptions, but I chose today the intersection formula by Odaka and Xiaowei Wang. It is described by this kind of intersection formula. L to the n is the volume. This is regarding the divisor, and take the intersection number of n times intersection stuff. So it's the number, and it's called volume. Or just consider C1L to the n. Or S bar is the average of the scalar curvature, and Kx over P1 is the relative canonical line bundle. So this divisor or first term class, second cohomology class, and take the intersection number on carry X over there. And this L to n plus 1 also intersection number. This is the Donaldson-Stark invariant. And a polarized manifold XL is said to be K semi-stable if this this invariant is non-negative for all ample test configuration. This is the important part of the definition. All ample test configuration. So you have to test many test configurations to check this inequality. And K polystable means equality only holds for a product test configuration. So this kind of product action, the sister action is a diagonal action to this and this. And polarized manifold is said to be K stable if this invariant is positive for all ample tensor coefficients. But ample is also a keyword in this lecture. So for final case, we take L to be the anti-canonical line bundle, this positive line bundle. So Yao-Tian-Donaldson conjecture says that on a polarized manifold XL, there will be a CSE K metric if and only if XL is K polystable. The difficulty is just as I said again and again, that we have to check the whole set of test configuration. This is the difficulty. And there are many approaches to study the whole set of test configuration using geodesics, iterations, variations, and also functionals and their slopes. And K-Einstein matrix was given by Chen Yang in 2015 publication year. A final manifold X admits a K-Einstein metric if and only if the pair of Kx inverse is K, and the only if part is due to Bellman and Bellman-Davis rule. And data security chains from one and also gave other proofs, but all these proofs use Chiga coding theory on Gromov-Hausdorff convergence and the rich curvature bound. Now, on the other hand, Bellman, Buxon, Yonson proved the variational method without using Gromov-Hausdorff convergence. That final manifold X admits a unique K-Einstein metric if and only if X satisfies uniform D stability or uniform K stability. So this is without using Gromov-Hausdorff convergence. This case is automorphism group is discrete. And then, so let's So I'll describe their result. What uniform stability is. So this is the model case for CSCK case. This is a very successful case. So I'll not. I'll review this first. For omega fixed scalar form, and I write H omega to be the function V such that omega V, which is omega plus I delta V, is positive. I regard this as a space of scalar forms in the fixed cohomology class. Strictly speaking, I have to mod out by constant functions, but I ignore that. And then this the space of scalar forms, and Ding energy is a map on H defined by two functionals. L is log of exponential minus u plus f to the m. F is the Ricci potential. So if F is given by fixed omega. And E is the something known as Monge-Ampere energy, also known as Obama-Bucci energy.
I really protest that you guys for thing any.
Yes.
You formulate it and call it different name, which I feel really bad.
Yeah. I saw your proof of that.
It's my first proof, and you're still there.
Yeah. Well, I follow the people's terminology. If I change people, yeah. Okay. I try to. And so Ring energy is said to be coercive if this and this D I defined, and did I define this, and J is something called Aubin's J function. This appeared in Aubin's paper. Maybe it is people call this. I agree with you, but I follow other people's terminology. And this also I function, but this is good in the sense this has a slope. I write down the slope later. This, and it is when D has a good convex along subharmonic geodesics due to Berndson. And if U is an absolute minimum of D, then U is a Kähler-Einstein metric. And this is a typical case when X is projected space, the Sobolev inequality of exceptional type in the famous Aubin's book. It's well described. Also, Mozart including this is the motivation to introduce D, probably. And so for an ample test confusion, we choose a metric on this L on X, which I write HS to be exponential minus 5s, and L is relatively ample, so the curvature of HS, which is delta above phi s, is positive definite. So we consider HS as the Kähler potential. So we get a ray of Kähler potentials, and then we insert. So I also change parameter from T to S in this way, and then when T goes to 0, S goes to infinity. So the central fiber X approaches central fiber, then S goes to infinity. And then the limit, if this inequality holds, then the derivative at infinity and important is that this exists and can be computed. And actually, for D has L part and E is given by this intersection number. And it is often denoted by E and A of XL for this test configuration. And the L part is described as log canonical threshold. This is the this computation rate, this theory to birational geometry, but it is denoted by L and A. I wrote down precise definition, but I don't want to take much time on this. But so the log canonical threshold appears as a birational geometry, but this in view of analysis, this sheaf gives a measure on the sky and possible are these divisors. This is divisor, and then the measure is finite or not along the divisor. It is detected by this log canonical threshold. This is the connection between analysis and birational geometry. So anyway, it is computed, exists and can be computed. This is important, and so this derivative at infinity, which we call slope, is given by some invariants that can be computed explicitly, and which are D and A. NA is short for non-Archimedean geometry. This was used by Buxton Jansson. And so there are I function, J function. J function is preferable because its slope can be expressed again as an intersection number, topological invariant in this way. And this slope is denoted J and A. And NA is short for non-Archimedean. Non-Archimedean geometry is will not treat today. And a Fano manifold X is said to be uniformly D-stable if there is an epsilon such that this inequality holds. And for any test configuration, XF. So what we want to see from this inequality is the behavior tends to infinity. So I didn't, maybe I forgot to mention that this is important, but the J function, this plays the role of normal H omega, distance from omega to other scalar form. For J goes to infinity, it goes to far away from in the space. So D energy. So So we say D is proper if D goes to infinity when J goes to infinity. So in the space of Kähler forms, Kähler form goes to infinity, then D goes to infinity, then we say D is proper. And so coercivity is a more precise version of this properness. So also this uniform stability is an asymptotic description of coercivity or properness of D ring energy. So if you want to have a solution of PDE, you want to find a critical point of function. For function goes to infinity and convex, you have a unique critical point. This is the idea, but this space is infinite dimensional. The problem is not so simple. But Bellman, Buxton, Johnson proved this uniform version of ERT and Johnson conjecture. Statement is on a Fano manifold. There is a unique Einstein metric if and only if X is uniformly D stable. This is equivalent to uniformly K stable as defined below. So this is the statement. This is uniqueness. Unique existence is equivalent to D stability. So in this case, automorphic group is discrete. So they used D function. This is a better property than Mabuchi functional. In the sense it has a better continuity as long as we consider Munjampe equations. But Mabuchi energy, so so we next turn to CSCK case. In CSCK case, this D function is not useful. Mabuchi energy is more useful, and K stability needs to be defined next. But in this final case, they are equivalent. Now let's turn to Mabuchi K energy function. This also has different description, but I use something called Chen-Pian formula. It is described by using three functional and E reach. H is something called entropy, defined by this, and E this as before, and the E reach is replace one omega by E reach, and the other term is the same. This this is the description for Mabuchi K energy, and E and E reach are relatively simple. This is linear along geodesics. The difficult part is this entropy. Entropy is hard to treat. And as before, M is said to be coercive if this inequality holds. Again, this wants to describe that if J goes to infinity, M goes to infinity. So it's like proper. Proper. If this is satisfied, it's proper. So M is proper, infinity, and constant. And this coercive in this inequality holds. So coerciveness is more precise version of this properness. Coerciveness is more proper version of properness. And again, for ample test configurations, we take ray or matrix along the fibers of L of X, and ampleness. By ampleness, we can take the curvature positive. So del del bar phi s is positive, so we can consider phi s as a family of scalar potentials, and then consider their behavior of M and J. If that inequality holds, we should have this inequality. And then again, this the slope or derivative at infinity is computed as well. In the next slides, this is due to Buxton, Johnson, Schultz, Dirichlet, and denoted NA means non-Archimedean. And so the non-Archimedean function, what they call this, is computed this way. The precise formula is not so important in this talk, but the point is that it exists and can be computed by this kind of topological data. So that's, I escaped the detail, but it exists and computed. This is an important point here. And Fano manifold is said to be uniformly K-stable if there's epsilon such that this inequality holds. This is a weak version of coercivity or properness. But we have to check for any test configuration. This is uniform K stability. And DF and MA is of this relation. So X0, the central fiber is reduced, they coincide. Otherwise, it's bigger than y equals 10, bigger than y equals to F, or equal to MNA. And so in the theorem of Baumann, Buxton, Johnson, I stated previously, the group X is discrete, automorphism group, unique. It's unique. So in this case, in their case, this X is discrete, and Chi extended their result for non-discrete automorphism case. So Chi considered a reductive subgroup of the identical component of OML. OML is the automorphism of X that lifts L. Identity component and take a reductive subgroup. He considered test config G equivalent test configurations. So what he assumed, so G of course acts on XL, but it also acts on this test configuration XL. Commute XL originally had a sister action, and we assume G action commute with the sister action on XL. Outside central fiber, XL is a product, and then in this case, this G action is the original action on XL. So this is G equivalent test configuration to extend Buxton Johnson to non-disputed automorphism group case. And GD also extended J non-Archimedean J function in this way. He modified using a Xi twist. A Xi is an element of T, and Xi twist of test configuration is just a twist of sister action on XL by this exponent T. So this is Xi twist of XL, and then he consider all Xi twist and take the infimum. This is JT and A, and then G uniform K stability is defined by this inequality for any test configuration. Okay, in this case, my scale is always ample, but we can modify this to any polarized manifold. So so this is G uniformly K stability. You can replace M and A by D and A, and you can define D uniform D stability too, G uniform D stability too. And this is a setup, and Chi Li proved the following. A Fano manifold X admits a K-Einstein metric if X is G uniformly K stable, or of course equivalent to G uniform D stable. And the question is whether the converse holds, but if G contains the maximal torus, then or the automorphism of X, then the converse also holds. So when G contains the maximal torus, then this is necessarily a sufficient condition for the existence. So and then combining the Chen-Donaldson sum, this condition should be equivalent to K polystability, but Liu, Xu, Zhuang proved that on Fano manifold, if G contains the maximal torus, then G uniform K stability is equivalent to K polystability using the Donaldson-Stacking variant. So combining these two, we get another proof of Gaussian-Donaldson conjecture for Fano manifold, independent of without using Gromf-Hausdorff convergence. So this is a story about Fano case. And then we want next time to CSCK case, on weighted external parametric test. The main case is CSCK case. First, I mentioned that analytic characterization was given by Chen. It's difficult to pronounce for me without G or with G. And proved that for polarized manifold, the properness of multi-energy is equal to CSCK metric. And then after his work for Fano case, he proved the following result. On a polarized manifold, if X is G uniformly K stable for models is another keyword here, implies the existence of CSCK metric. What is models? Model is something non-ample test configuration. So he defined a model of XL which satisfy all the conditions of test configurations except the ampleness of L. So we do not assume ampleness. And then we say XL sets to be G uniformly K stable for models if XL satisfies this uniform condition. So this is the meaning of this. So this uniform condition is satisfied for wider class of test configurations, even non-ample test configurations. Then CSCK metric exists. This is CD proved. So again, we remove the ampleness of test configuration. We say X is a model for wider class of test configurations satisfy this inequality, then there is a CSCK metric. So as I said, the larger class test configuration satisfy uniform condition. It means it is stronger than uniform K stability. So in this definition, we assume G, where is G? Sorry, I lost G. I said G is a reactive subgroup of identity component of XL, and then the recent paper by Brooks and Johnson that appeared last year proved that the converse of G leads without holds when G is all 0 except. This is naturally we assume this is reductive. This is a natural assumption in view of Dictionary-Witt's Matsushima theorem. So the converse means this. So Chidi proved this direction. This direction also falls if G is full automorphism. Sorry. So this is the statement of Chidi and Brooks and Johnson. So let XL be a polarized scalar manifold. The following conditions are equivalent. There is a CSCK metric in the first chunk class of L, and G is of 0, and we assume it is reductive. It's natural assumption because of Dictionary-Witt's Matsushima. And XL is G uniform K stable with respect to models. They are equivalent. So as I said, this direction is due to 2 to 1 is due to Chidi, and Brooks and Johnson in the other direction. But this is not. This statement is not stated in this paper, but combining their result, we get this result. Their result, sorry. Oh. This Brooks and Johnson's result is stated in terms of non-Archimedean pluripotential theory. So this is something hard to explain. Let's review the pluripotential theory since studied by Bedford Taylor. It's not very new. It's again 50 years ago. For non-smooth pluri-subharmonic functions, that the wedge product of currents makes sense. So we can consider a Monjamp equation for currents. So this is the one studied recently. This maybe I show this people. Where is it? Oh, like the Guage JI looks on SCD Guage JI. Those people began to use this pluripotential theory to study singular sort of Monjamp equations. And then the omega pluri-subharmonic functions we can consider wedge product currents, and then they introduced the class of pluri-subharmonic functions satisfying this equality. Normally this inequality, but full measure once they put epsilon, E maybe, and E1 to be the L1 functions in terms of this measure. And this was useful in the study of their work by Guage, Deriai, Cookson, Institute, Guage, Deriai, those people. And Darvas defined D1 distance and proved that the completion of the space of Kähler forms with respect to D1 is just E1. This was an important step for their work, and function E is D1 continuous. So D1 is equivalent to J function actually as a distance on H. And this is just a motivation to explain non-Archimedean geometry introduced by Brooks and Johnson in their work. So Brooks and Johnson consider H and A to be the space of all ample test configurations of Excel, equipped with a naturally defined Darvas metric D1 and A. They showed such a metric can be considered on the space of all ample test configurations. And then E1 and A is the metric completion of H and A with respect to D1 and A. And M and A extends to E1 and A as a lower semi-continuous function. So E1 and A is a completion of the space of all test configuration. So there are more sort of singular test configurations. And E1 and A contains models. And they define a polarized manifold Excel to be K-hat polystable if M and A is non-negative for all phi in A, with the equality holds phi is a product test configuration. A uniform K-hat polystability if OL is reductive and there is an epsilon such that this inequality holds. This is distance between phi and the subspace of real test configurations. So this is the condition they wrote. And for the CSCK problem, they proved the following. Brooks and Johnson by last the same paper as I mentioned. Polarized manifold XL, the following are equivalent. There is a CSCK metric is C1L, and XL is K hat polystable, and XL is K hat polystable. And the result, this result is extended to weighted extremal case. We need to modify these conditions properly, appropriately for weighted case. So I'll not do it here because it's a bit complicated. So I just mentioned.
Yeah, okay, sorry. Yeah, I think we are on 10. So how many minutes do you need more?
Maybe 1 minute.
Okay, thanks. Thanks.
So their statement is log concave. If V is log concave, the following are equivalent. So just ignore suitable modification. VW weighted extremal exists. Suitable modification of K hat polystability and uniform K hat polystability, they are equivalent. So this is their result. I will not talk about this suitable modifications. Maybe may I have 2 minutes? So there is another paper by Davas and Zhang, Kue Zhang appeared around the same time, and they modified entropy part by this functional, and they introduced modified Mabuchi functional in this way. And the entropy had a problem, a difficulty, but replacing this, this function has easier to treat. And then they can compute the slope and also define uniform stability. They showed that the following are equivalent. There's unique CSCK metric, the uniform K beta stable for K beta. K beta stable is just this inequality. But this is better because they only consider ample test configuration. They do not need to test configuration. They can only consider ample test configuration and define this uniform stability and gives a characterization of the resistance. So I'm not going into detail. Let's finish.
Okay, yeah, probably because of time, but there's one more question, if it has.
Thing has made no contribution to the subject.
I think.
Okay, yeah, if no question, let's thanks to the speaker again. Yeah, okay, let's come back at 11:25 because of time.
7:30? Yeah, it is. Yeah, because the flight is 7:30. Yeah. Well, are you coming back? I hope so. All right. So is it shifted by 10 minutes?
Yes, that's right. Okay. Yeah. So yeah, are you ready?
Yes.
Okay. Okay. So yeah. Let's start our Okay. Today's last talk, and the talk is given by Valentina Tassotti, and the title of his talk is Immortal Solutions of the Cantor-Ricci Flow. Okay. Let's welcome.
Okay. Thank you. So thank you very much. So obviously it's a great pleasure to be here and speak at this wonderful conference. I'm sorry that I arrived a bit late, but better late than never, right? So what I will talk about is about Ricci flow and Kähler manifolds. And it's an overview of two papers I recently wrote, one with some combination of this author, one with Hein and Lee, and one with Lee and my postdoc, Zhang. So let's start with some background and basics. So this again a Kähler talk. So X would be compact Kähler manifold without boundary, N would be the complex dimension, and just some notation. So the cohomology, the cohomology H2, the usual de Rham cohomology, has a subspace that I will call H11 of the de Rham classes of closed real 1-1 forms. So invariant under the complex structure if you want. And the point is that if I have a Kähler metric on the manifold and I take the corresponding Kähler form, omega, then the de Rham class of omega belongs to this subspace because omega itself is a closed real on 1-1. And so if I take all possible Kähler metrics, by the way, Kähler form and Kähler metric would be interchanged. So if I take all possible Kähler metrics on X and look at all the possible cohomology classes of the corresponding 1-1 form, I obtain a subset in H11, which is easy to see is a cone, and it's convex, and maybe with a slightly more work, you can show that it's open in the Euclidean topology. So this cone is called the Kähler cone. Here is a picture stolen from Desmailly's slides. And the closure, so it's an open cone. The boundary sort of picture here is not part of it. And the closure is usually called the NEF. This name comes from algebraic geometry. It's actually an acronym, so it doesn't have any meaning in English. And this NEF cone will be important, as you will see in 2 slides. By the way, the boundary of this cone, I picture here as polyhedral, but this is not the case in general. It can have an extremely complicated shape. The faces, it may have some faces which are not defined by polynomial equation, maybe not linear necessarily. And the faces could be infinitely many and accumulating somewhere with fractal structure. So this picture is way too simple, way too simplistic. But in any case, it's the boundary of an open convex cone. Now, when you have a Kähler metric, the Ricci curvature form, the Ricci curvature in Riemannian geometry can be naturally identified with another closed real 1-1 form denoted by Rich. So the coefficients are basically the Ricci curvature. And it has this wonderful formula in local holomorphic coordinates. It's 2 complex derivatives, the IDD bar of log determinant of the metric up to a minus sign. So this formula underlies a lot of magic in complex geometry. In particular, you can see that this real 1-1 form is locally exact. So for sure it's closed. And also, if you take 2 different Kähler metrics and take the difference of the Ricci forms, this term here, when you take the difference, you get IDD bar log of the ratio of the determinants, but the ratio of the determinant is a globally defined smooth positive function. So the conclusion is that the difference of 2 Ricci forms is globally exact. Therefore, the cohomology class in the Rham cohomology, say, is independent of the metric. So this was observed by Kähler already, and it's a special case of a theorem of Chern. So usually this is called the first Chern class of X up to this factor of minus 2 pi. So, all right. Now, Ricci flow. So I will be working only on Kähler manifolds. So the story of Ricci flow is much more general than this, but I'll just specialize right away. So Xn will be still compact Kähler. Omega 0 will be the initial Kähler metric. So if I have a solution of Kähler Ricci flow, it's just a solution of Ricci flow starting with that initial metric. And it turns out, as observed in Hamilton's first paper, that the evolved matrix, if you start with a Kähler metric and you evolve, it's still Kähler, and with respect to the fixed complex structure. And so you can denote it by omega t instead of gt. They solve the Ricci flow equation. Here I have renormalized it by a factor of 2, just because the factor of 2 was there for aesthetic reasons in formulas. And then in the Kähler setting, this formula, for aesthetic reasons, it's better without the 2. So it's just speeding up by a factor of 2 or slowing down. So dg dt or the omega dt is minus Ricci, and the initial one is the given one. And of course, Hamilton proved in more generality, and then Huaidong was the first to study the Kähler case. So they proved that the Kähler-Ricci flow always has a unique solution for some positive time. So you have well-poserness of this flow, and we can denote big T the maximal forward existence time, which may be now plus infinity. So a nice thing that happens in the Kähler case is that there is actually a formula for this maximal existence time. So you can find it by looking in cohomology. So this is again the flow equation. It's a equality between closed real 1-1 forms. So you can pass to cohomology classes. Now the right-hand side is independent of T by that observation of Kähler from before. And so in cohomology, you just see that you move along a segment. So the cohomology class of the flow, as long as it exists, is given by the initial minus T times this fixed one, 2 pi C1 of x. So in cohomology, you move along a segment. Here is a picture of the initial class. Here is the Furchan class. And this would be the picture of the flow in cohomology. And as long as the flow exists, this segment has to stay inside the blue cone because omega of t is a Kähler metric in this class, the evolving one of the flow. And the converse is true as well, as was proved in, again, increasing layers of generality by Huaidong, Tsuji, and Tian and Zhang. The maximal existence time is exactly how long this yellow segment stays inside the blue cone. So the supremum of all t, positive for which this segment stays inside the Kähler cone. So it's an interesting theorem. After you figure out that it should be true, it's not super hard. You just apply basically the parabolic version of Yao's estimates to this. So the fact that you are inside the cone gives you basically a sub-solution, and then from there you can get it. So in particular, from this formula, you can see immediately when is this plus infinity with some simple, well, you can see it in the picture. This yellow direction has to be inside the closure of the blue cone. So you have to move in the direction of the blue cone. So that's equivalent to saying that the minus the first-term class belongs to this Neff cone. And the interesting fact about this corollary is that the left-hand side a priori depended on the initial metric omega 0, right? Given omega 0, you have big T. But in fact, the right-hand side does not. So the condition whether the flow is immortal, so immortal means that it has infinite existence, is independent of the initial metric. So if you have one, which is immortal, then every other flow on that manifold is immortal as well. And okay, so these are the ones in the title. Okay, so when you're not immortal, then you see something like in this picture where you hit some point on the boundary in finite time. So those would be called finite time singularities. They're also extremely interesting, but this talk will focus on the immortal case. So what I want to know is basically what happens when t goes to infinity. So you suppose you have an arbitrary complex manifold with initial metric and it's immortal. The ultimate goal would be to understand the behavior when t goes to infinity. So you can start with some explicit examples and simple calculations first. By the way, this is called Neff canonical bundle. So I didn't define the canonical bundle, but it's, if you know complex geometry, some vector line bundle whose first-term class is this minus C1 of x. Otherwise, it's just a terminology for this condition. So there are many manifolds that have this property of this Neff canonical bundle. Tori, so complex tori here. Riemann surfaces of genus 1 or higher will have this property. Hypersurface in projective space, smooth hypersurfaces of given by one homogeneous polynomial, the zero locus of one polynomial of degree at least 10 plus 2. And then this class of manifold is closed, for example, under taking products. And this operation already suffices to give me plenty of examples. So just to say that it's a very rich class of manifolds, but it obviously does not include everything. So, for example, the Riemann sphere or CBN is not in this class. So there you have a finite time singularity. Okay, so the next thing to do is to compute whatever you can compute on these flows. And the easiest thing to compute is the volume, the Riemannian volume of the evolving flow. I suppressed some factors of n factorial, which technically would be needed, but are useless in these formulas. So up to some factorial universal constant, the volume is just the integral of the evolving Hiller form wedged with itself n times. But by Stokes' theorem, it only depends on the cohomology class. So I can write it in this form. This would be, if you want, the pairing between this cup product of this class and the homology fundamental class. And then this one is clearly a polynomial now in T. So you can just expand it out. And it's a polynomial of degree, let's call it M. And this is the first coefficient. And then there's some lower order terms. And what is M? M, well, it's the largest number for which this integral is strictly positive. It turns out to be the same as the largest number for which this minus Fortune class wedged with itself m times is non-zero in the RAM homology. So you just this is something you can easily compute. Given a Kähler manifold X, compact, standard techniques will allow you to compute this class, minus C1 of X. And then presumably you are also able to compute the cohomology. And then you can check this condition. You can compute this number m. And it can be done in practice. So it's, I guess, obvious from the definition that it is between 0 and the dimension of the manifold. So summary, if you have an immortal solution, the volume always grows polynomially. The degree is this special number, little m, sometimes called numerical dimension, because it wants to be some kind of dimension, but it's potentially lower than the actual dimension of the manifold. So I maybe mention it here, although it's not really super relevant for most of the talk, but it's good to know that recently, like 2 years ago, Guo, Fong, Song, and Sturm proved, actually this was a long-standing problem, that if you rescale the flow, so omega t divided by t, here I'm thinking that t is large, so I'm not looking at t near 0, okay? Then if you rescale the flow like this, the diameter of this Riemannian manifold is uniformly bounded from above. So this diameter bound was a nice application of the technique of auxiliary Monge-Ampere equations. So that's something to keep in mind, but not directly relevant for now. Now, next, you can start to study in more depth what happens. And you have this discrete invariant, this numerical dimension m, which can take the dimension plus 1 values. Makes sense to study it in cases, so split the discussion. And 2 cases are easier. So the by now easiest case is the case when the numerical dimension is 0. So if you forgot, it means down here, oops. It means down here. So if this m is 0, it means that already C1 of x must be 0 itself in H2. So that means that the first class is 0. That's what we normally call Calabi-Yau. It's a kind of relaxed, weak definition of Calabi-Yau, but that's the one we are going to take. So it vanishes in a real cohomology, H2. So in this case, I believe it was Huaidong's PhD thesis. He proved that the flow converges smoothly in the infinity topology, in fact, exponentially fast, to a Ricci flat metric, so a Kähler metric on X with 0 Ricci curvature. And it's the unique Ricci flat metric cohomologous to the initial one. So the flow in this case does not move the class, as we discussed. And these metrics, of course, were coming from the solution of the Calabi conjecture proved by Yau in '76. So this is the parabolic version of the solution of the Calabi conjecture. So this is the best possible scenario. So smooth convergence and everything is perfectly nice. The next case is the opposite, when the numerical dimension is maximal. Again, if you go back, you see that this means that, and you drop this one, this integral with the m equals n is strictly positive. So this is, again, something very easy to check. This has even a name called the minimal of general type. So these kind of manifolds are being studied a lot. And the prototypical example would be a Riemann surface of genus 2 or higher would satisfy this, while a Riemann surface of genus 1 would be Calabi-Yau, the previous one. And then here again, Huaidong and then Hajime Tsuji, they proved that now you do need to rescale omega t by t, and this would be basically throughout the whole talk. If you rescale this, you again have smooth convergence, but away from proper closed analytic subvariety that I will define in a second, and to some limit in metric omega infinity, which is scalar, away from this sigma, and is satisfied the Keller-Einstein equation. Ricci is identically equal to -1, so constant negative Ricci curvature. Now, what is the sigma? This bad set where you don't have smooth convergence is just a union of all irreducible analytic subvarieties closed, for which, say, the volume is shrinking to 0. So you compute the volume with respect to omega t over t of all possible closed irreducible analytic subvarieties. Just think compact complex submanifolds if you don't like subvarieties. Look at the volume of all of them. It can be computed cohomologically, and you look at the ones whose volume is shrinking to 0 at infinity. That's exactly the same as this condition here, some cohomological condition. So you can determine this set a priori. It's non-trivial that this big union is itself proper closed analytic. A priori, it's an enormous union of closed analytic things, but it's actually itself closed. It's empty if and only if minus the Ferchen class is in the Kähler cone. So this is the case which was considered also by Yau and independently Oban, where they constructed this Kähler-Einstein metric on X in this case. And then in general, under this assumption, this sigma may be non-empty. And then you'll have this Kähler-Einstein metric, but only on X minus sigma. And the convergence is away from that. And I didn't write it, but you can also ask about the Gromov-Hausdorff convergence globally as metric spaces. And the answer is it's the metric completion of X minus sigma with this omega infinity metric. So the global limit is just a completion. Yeah, I think so. So the one with singularity, you mean, right? Yes, I believe so, but not. It was not me. I think it was done. Again, maybe Tsuji also first for the static case. Yeah, I'll take a look, but I'm pretty sure it was done. Yes, like the Chern number inequality for this. Oh, okay, okay. Yeah, actually, I don't remember. So I'll take a look. Yeah. You're sure it's not done? Okay, then that's something else.
Because the convergence you have is not strong enough.
It's not strong enough for sure. It's only on compact sets. It's nice. Yeah. Okay, that's a good question. Also, yeah, but not about the flow. It was Calabi-Yau. Yes. So all right. So we're left with all the remaining cases, which we can bundle all together with the numerical dimension strictly between 0 and n. So this is the last one in some sense. And sadly, it's by far the hardest case. So here, there is a conjecturally, the manifold has a fibration structure. So this is part of a famous conjecture called abundance. In fact, it's the transcendental extension of a conjecture in algebraic geometry. Since I did not assume anything was algebraic, it says that if you have this condition of a Neff canonical bundle is equivalent to having a nice sort of fibration structure called the semi-ample canonical bundle, means that your manifold has a surjective holomorphic map with connected fibers onto some lower dimensional projective variety y. The dimension of y, I guess it's written somewhere else. Yes, the dimension of y is actually this m. And the first minus Ferchen class is the pullback of basically a Kähler metric from the base. So more precisely, what does it mean? It means that if you remove the critical values of this fibration together with the singularities of the base, and you remove upstairs the preimage, which you can call the singular fibers, then if you remove this kind of a discriminant downstairs and singular fibers upstairs, you have a very nice proper holomorphic submersion from X minus a singular fiber to Y minus a discriminant. And these fibers are compact Calabi-Yau and pairwise diffeomorphic, but in general, different complex structures. So basically, abundance is telling me that whenever you have an immortal solution, you're always in this fiber situation. The two previous cases are the degenerate cases. When m equals to n, this map is birational, so x and y are almost the same. It's just that this sigma set gets contracted. When m equals to 0, y is a point, and x itself is Calabi-Yau. It's just one fiber of the map. So those are the degenerate cases. And this is a case where you have an honest fibration. When I say fibration, I allow singular fibers, so like here. Right, so this conjecture is known in low dimension, but otherwise it's still widely open. And we're not going to assume the conjecture, but we're going to assume that we have this semi-ample canonical bundle. So that's saying that we're studying a subclass of the immortal solution, which conjecturally is everything. So, all right. And I will say something maybe at the very end about what if you don't have this vibration. So, okay, so that's the setup from most of the rest of the talk. So what is the simplest example? The simplest example will be m equals 1, n equal to 2. So the total space is complex 2D. The fibers are complex 1D. The base is also complex 1D. These are called elliptic surfaces or minimal proper elliptic surfaces. And the simplest ones are just products of a one-dimensional torus, complex one-dimensional torus times a Riemann surface of genus 2 or higher. And you think of this as mapping onto the sigma g. So the sigma g is the y. And the fiber, which are Calabi-Yau, is this torus. In this case, you can write down an explicit solution of the flow, if you want, by taking the product of the pullback of the Poincare metric on the hyperbolic Riemann surface and a Euclidean or flat metric on the torus. So you pull them back here and you take the product. So here I normalize the hyperbolic metric with Ricci -1. Then you can just see explicitly that the flow starting at this product metric is still a product, and it's given by this explicit expression. And if I do omega t divided by t, I see that it converges smoothly to this degenerate metric. This omega p is the pullback of the Keller-Einstein metric, hyperbolic metric from this factor. And it's trivial on the torus direction. So you have a kind of a collapsing picture. So this is what we're trying to achieve in general. And so if you go back to full generality, it was known that on the base minus the discriminant, there is a nice metric, omega infinity. Kähler, it's basically Keller-Einstein. The Ricci is -1, but it has a twist. So there's an added term to the Ricci curvature called Weil-Petersen form, which is semi-positive definite. So it has a sign, and it encodes the variation of the complex structure of the smooth Calabi-Yau fibers. So this is the analog of the Keller-Einstein metric we had before. And it's also known that if you do omega t over t, then in the weak topology as currents, you converge to the pullback of this omega infinity. So the natural question is, can you converge in a better sense? So this weak convergence is extremely weak. It doesn't, for example, have any nice geometric applications. So the first main result is that indeed you have smooth convergence on compact sets away from the singular fibers. This flow exactly shrinks. So a renormalized flow, omega t over t, shrinks the fibers at least away from the singular ones in the smooth topology. And you converge to the pullback of this limiting twister Keller-Einstein metric. And to be clear, the smooth topology with respect to some fixed Kähler metric, such as the initial one. So this is the schematic picture. And this result with Hein and Lee has a long story, so I'll try to summarize it briefly. So there is an analogous problem in a static case where you have a family of Ricci flat metrics on a Calabi-Yau, and you change the cohomology class along a similar looking segment, and you assume you have a fibration. So one can set up things similarly, where instead of Ricci flow, it's just Ricci equal to 0, static, but depends on a parameter. And then that's what I studied first. That's what Yao was asking before about my thesis. So that was the original problem. And indeed, that one I did solve eventually. So the final result was with Hein a few years ago, after a paper with Mark Gross and this Yuguan Zhang and then other stuff with Hein. And the point is, after you do the static case, which is an elliptic family of elliptic equation, you can imagine that perhaps you can add d by dt into your proof and make it parabolic. So this is actually correct. Sometimes it takes a lot of effort to add this d by dt. So this was done. The theorem above was proved by Fong and Zhang and Hein and myself when the smooth fibers are tori, adapting the original paper with Mark Gross and Zhang. Then later Fong and Lee adapting another one with Hein and myself when the smooth fibers are all isomorphic. And then Holder convergence by Chu and Lee, again adapting our work. And finally, the one that I want to discuss is also the adaptation of this paper with Hein and myself from 21. So the adaptation turned out to be quite non-trivial. That's why there is a 3-year gap here. And I will mention a few details, probably kind of without going into too many technicalities, to give a rough idea. So the way we prove this is actually by proving an asymptotic expansion for this flow, a rescale flow, with uniform a priori estimates up to any fixed order that you want. And it's proved by a contradiction and blow up. Actually, it was originally inspired by the proof of the Schauder estimates by scaling by Leon Simon. So that was the source of all this meta idea of trying to prove estimates by contradiction, blow up, and reduce into a Liouville theorem. And here the Liouville theorem was proved earlier. It's a Liouville theorem for a Ricci flat matrix on cylinders. It's the one that we use. Okay, so I do want to tell you a little bit about this expansion. So it's not some kind of formal microlocal theory expansion type, but it's really something with estimates more in the spirit of Yao's original paper. So for this, you try to understand. So basically, from previous work, we have the kind of zero order behavior in the limit is this pullback of the metric from the base, and you can understand also the first order behavior. It's something called a semi-Ricci flat form. Namely, I proved with again long time ago with Yuguang Zhang that if you restrict to a fiber. So the flow without normalization is sort of expanding. Remember, the volume is growing. But if you restrict to any smooth fiber, you actually converge smoothly to a Ricci flat metric on the fiber, the unique one in the correct class. So the flow is expanding the base direction, but it's not expanding the fibers. It's actually converging perfectly nicely on the fibers. And these Ricci flat metrics can be somehow patched together into a global 1-1 form upstairs. This 1-1 form does not extend across the singular fibers, so it only exists on X minus that. And when you restrict it to each smooth fiber, by construction, is this Ricci flat metric. So this is a semi-Ricci flat form, will be the terminology. And one can show then the flow to first order, to zero order, it's this pullback from the base. And the first order correction is exactly this semi-Ricci flat term. And then you want to understand the next order or the remainder. So the theorem looks like this. You are given a number k, which is how many derivatives you want to control, and it has to be finite. So right now we don't have an expansion that goes to infinite order. And some small ball on the complement of the discriminant locus, which is arbitrary, sufficiently small. Then on the preimage of the small ball, the flow can be written as an expansion. As I said, the first two terms are what they are. I will explain these terms in the next slide, but there is basically a term from the base, which is some kind of a zero order Fourier mode, as I will explain. And then you have a k or up to k terms, and then a remainder, a final remainder called eta. And these have estimates. In fact, they go to 0. So the one from the base goes to 0 in the C2k topology on the base. And the gamma j's go to 0 in the CK topology upstairs. And why do they split them? Because they actually go to 0 at different rates depending on the value j. But if you don't care about the rate, you could have just lumped this all into one term. And that's not what we do. And then the final term is much better. The final term goes to 0 in C2k with respect to the shrinking metric. So these are basically pullback from the base plus tiny times the fiber. It's a very small metric in the fiber directions. And it's very hard to bound derivatives when you penalize the fiber directions very small So the fact that you can achieve this means basically that this eta k decays in the Farber direction. So this is a very strong estimate. And the point is that this remainder satisfies the very strong estimate, but these intermediate pieces do not. They are bounded only in the fixed metric, not in the shrinking metric. So I will explain a bit more in the next one. And in the previous easy cases, when the smooth fibers are tori, or the fibers are not tori, but they're pairwise isomorphic to each other, it turns out that all these intermediate terms vanish completely. And then you can say that the flow really looks like the 0 and first order term, and this decays in all shrinking CK norms for all K. So this was the best case scenario that we proved in the earlier papers. And however, in general, there are these obstructions, two finite order obstructions. So I explained slightly more how to find them. And then we go back to the kind of high level overview. So they're just two slightly technical slides. Feel free to ignore if you don't want to know the details, but just a little bit. So the point is the omega t over t is cohomologous, let's say away from the singular fiber where everything makes sense. You can write it as this reference plus dd bar of a function. And omega tilde would be the notation for this reference metric. And so the theorem was saying that the CK norms decay. In fact, we proved that the CK alpha norms are bounded. And then from the proof, we will follow that the CK norms actually decay. And for technical reasons that you see here, we only deal with even order derivatives. This is because the parabolic Holder spaces behave differently with respect to even or odd order. And the odd order somehow did not go well with our proof. So we removed them. So we only jump two derivatives at a time. So the first case would be zero derivatives. So here you just do the fiber-wise average of the Kähler potential with respect to this fiber-wise Ricci class metric. So this is the 0 order Fourier mode, and take dd bar. This is our gamma 0. So and we prove that in situ alpha is bounded. In fact, in situ it goes to 0. And then the eta 0 is just the difference. And then again, we proved that, actually, sorry, this is Chuli and then Hein and myself. We proved that this one goes to 0, is bounded in the shrinking Holder norm. However, when you go to the next level, this error term eta 0, sadly, is not bounded in the stronger norm, shrinking stronger norm. In general, it will blow up. So you're stuck. And the way to get unstuck is to find, by a rather complicated procedure, a finite dimensional space of obstructions. So here this I is from 1 to some big number. So some finite dimensional space, finite number of smooth functions. And you take some kind of projection of your solution onto the space of functions. And the projection is a bit technical, but you take start with this A, which is the fiber-wise L2 inner product between the obstruction and the trace of the dd bar of this, so the Laplacian of the potential. This gives you a function on the base, and then you multiply by this. So you do basically the component, and then take the green operator and apply dd bar. So looks like a mess. The point is that if you take the trace of this gamma 1, this becomes a Laplacian, the trace with respect to a shrinking metric, and this Laplacian inverse cancel, and you get back this projection. So the conclusion is that if you define eta 1 by subtracting the pieces, so this is the flow, you subtract the reference, you subtract the 0 order Fourier mode, and you subtract this gamma 1 here. This is the remainder eta 1. Its trace will be perpendicular to all these obstructions. This is what you get by construction. And then you set up an argument by contradiction where you want to prove a priori estimates for all these pieces, as stated on the previous slide, in these Holder norms. And this is an enormous blow-up argument, like I don't know, order of 70 pages. So really complicated. And this gives you the theorem to order k equals to 1. So that's 2 derivatives. And then the next order, you have to do the same. So you further decompose the remainder of the previous term as some projection onto some new obstruction functions, G2i, and then the new remainder. And you prove that the new remainder is bounded in the shrinking C4 alpha, and you continue. So the summary is basically for this part is that these obstruction functions, they will give you something, an obstruction to these excellent estimates that are shrinking in the fibers. And then the remainder will satisfy those. And this orthogonality is used at the very end of a blow-up argument to get a contradiction. So it's not apparent why it's useful. I didn't even say where these functions come from. So it comes at the very end of a blow-up argument. So, all right. So that's the first main theorem. And for the second one, it's going to be on the next slide. But maybe first I mentioned the curvature bounds. This is a kind of natural question. So you have now smooth collapsing away from the singular fibers, and you can ask what kind of curvatures will remain bounded under this collapse. So in fact, we are only able to talk about curvature on the nice region, away from the singular fibers. I will maybe say in a second what is known on S. So which curvatures remain bounded? So as a corollary of our theorem, in fact, we can prove that the Ricci curvature remains uniformly bounded. The bound depends on the compact set. So you fix a compact set away from the singular fibers, and there they are collapsing with bounded Ricci curvature. In fact, there is a formula for the Ricci curvature. It converges to the pullback of the one from the base. So the error goes to 0 in the C0 topology. So this means that taking Ricci curvature and passing to the limit do not commute, right? Because if I pass to the limit omega t over t, I get this omega infinity whose Ricci was minus omega infinity plus Weil-Peterson. But if I first take Ricci and then pass to the limit, the Weil-Peterson is gone. I mean, this is expected. So, collapsing limit does not commute with taking Ricci curvature, but you can identify exactly the commutator is this Weil-Peterson form. And by the way, I should say that the scalar curvature was known from before by work of Song-Tian to be bounded actually everywhere, even at the singular fibers. And it's an open problem whether the Ricci curvature also remains bounded at the singular fibers as well. On the other hand, if you want the full Riemann tensor sectional curvatures, then this happens even only if the smooth fibers are tori or finally covered by tori. This we knew from a long time. So in general, you have collapse with bounded Ricci, but very much unbounded sectional. So it's not like a Shiger-Fukaya-Gromov type situation. It's unless the smooth fibers are tori or finite quotients. And my student Kong proved just a few months ago that you can upgrade this theorem here to up to 2 derivatives of Ricci curvature, also remain bounded. These are derivatives in the shrinking metric and the GT over T derivatives. And 3 or more derivatives in general will blow up. So the fact that there's a critical number of derivatives, it's directly related to the previous expansion that has some up to C2 is good and more than C2 is not good. So this is coming from that. So yeah, so that's the second and last theorem I want to mention. This is more recent. Namely, can we identify the Gromov-Hausdorff limit globally? So the previous theorem says if you're happy to throw away a singular fibers and work on a compact subset away, everything is perfectly nice, basically, or understood. But if you do keep the singular fibers, the estimates blow up near there. So it's unclear what exactly you can prove. But you can still ask about convergence as metric spaces. And indeed, we do prove, this was a well-known open problem raised also by Song and Tian, that the Gromov-Hausdorff limit exists of the, again, rescaled flow, and it's just a metric completion of this base with this Twister-Keller-Einstein metric, and you take the metric completion. So it was already known that this Z is compact. I guess it follows from the diameter bound from before, but it was already known anyway. And Gabor Sekehidi, oh, sorry, I have a typo in his name, had earlier proved that this metric completion behaves like a Ricci limit space. It's a so-called non-collapsed RCD space. So in some sense has non-negative, has a Ricci curvature bounded below by -1, the one that you expect in the weak sense. And he proved that it's also homeomorphic to the base Y. Y is not necessarily smooth, right? It's a singular projective variety in general. And also that when you take this completion, if you remove the regular part, then what's left has a real Hausdorff codimension at least 2, which is not what you expect in general for collapsing in Riemannian geometry. You expect codimension 1. So here you gain 1 dimension. And so we use his result as part of the analysis. And I should also mention, I have proved a few years ago with Yang Li that this theorem is true when the base is smooth and this discriminant as a technical assumption of a simple number crossing divisor. So this method here was not good enough, but the ideas here are used. Also the ideas from Gabor, and also a very important idea from Guo Jae-Song's term, which allows us to get a Holder bound for the distance function of, oh, sorry, I didn't say, what is this D? D is the, yes, it's the D on Z, the distance function with respect to the background one. So it still remains to me, very interesting open problem to show that this RCD space is actually a more classical non-collapsed Ricci limit space. So it's a Gromov-Hausdorff limit of some smooth manifolds of the same dimension at Z with Ricci uniformly bounded below, and also with this non-collapsedness assumption, the one volume of Bose reduced 1. So this is unknown, except when the base is smooth. So when the base is smooth, you can prove this, but the singularities of this Y somehow prevent us from proving this. And however, Gabor did prove there is RCD non-collapsed, so it seems tempting to ask. So if this is true, it would actually simplify a bit our argument. You could throw away the RCD story. So we have to use quite a bit of stuff from the RCD technology, and you could throw it away. But right now we don't know this. So yeah, so this I think is the last slide. So as I promised earlier, you can ask now, go back to the original question. So I told you a long story, assuming that you have this vibration, like Kx semi-ample, basically assuming that the conclusion of the abundance conjecture is true on your manifold. So what if you don't assume that? So you now have a immortal solution. The only open case is when the numerical dimension is between 0 and n, but you don't assume that you have this vibration. So can you say something? So what you can say easily is that if you pick any sequence that goes to infinity, and you can always extract some subsequence such that the rescaled flow converges in the weak topology to a current, so-called closed positive current, omega infinity, which is in the correct cohomology class. So this is what you would like to say, the same limit as before. I conjectured recently, but it's kind of the obvious expectation, that this limiting current should be unique. So you don't need to, sorry, what do I mean? In two senses. One, that you don't need a subsequence. So if you take any sequence of time, it just converges to Kur, sorry, omega t over t converges. But also, then if you change the initial metric, you still get the same limit. So whatever way you start, you should always get the same limit in this weak topology. So it's not a very strong, this weak convergence is really weak, but somehow proving uniqueness seems hard, unless you can show that this satisfies some kind of PDE for which you have uniqueness, or you have some monotone quantity, something that forces uniqueness. Right now, we have none of the above, and so this is open. About Gromov-Hausdorff, again, the same nice paper of Guo Feng term, they proved that you can take subsequential Gromov-Hausdorff limits. This is not a trivial consequence of this Gromov precompactness, because along this flow, you do not in general have a Ricci lower bound. So you cannot just apply this Gromov precompactness. Nevertheless, they were able to prove that you do have a Gromov-Hausdorff limits, which are compact, but now they may depend on the sequence and the initial metric. So right now, you don't know that it's unique. And again, the natural conjecture is that it's also unique, and it should be homeomorphic to a projective variety of dimension m, simply because this is what happens if you believe this abundance conjecture. So you could ask many more questions, and you can either speculate whether proving this and some more properties of this current may help you to prove the abundance conjecture. Certainly, if you prove enough properties, you can definitely prove the abundance. So, but it's not clear that the flow was the tool to use. So it's one possibility. Certainly, if this is true, this omega infinity would be some kind of canonical object, purely associated to the complex structure, independent of any choice of metric or anything, and potentially useful for this. All right, so time is up, and thank you very much.
Yeah, so are there any questions?
Oh, yes.
Hello. In
Yes.
the if you go back a few slides, I think it was you
This
had
one, no.
the statement about, well, you could think of it like this expansion. Everything goes to zero except. So do you
Yeah.
know the speed of it tending to zero? Something more precise?
You mean, yeah, so all these guys go to zero. Indeed, the limit
Yes.
is this one, right? So everything here will go to zero.
Yes, yes, but
But-
do you know how fast they go
Yes,
to
yes.
zero in t?
Yeah, I didn't write it, yes. Ideally, what should be true is the following, that for gamma zero, this is the only one for which the rate is unknown. And I think there is some fundamental reason why we don't know the rate. The rate of this is obtained by some compactness and contradiction argument. So that I don't know. But for these ones, there are conjecturally sharp rates. They are supposed to be, I think, if I remember correctly, integer powers of 1 over t, conjecturally.
Okay.
But we don't know how to prove that. We can prove something a little bit weaker, but it should be an honest asymptotic expansion in, I believe, integer powers of this parameter.
It would be very beautiful.
Yeah, but I think perhaps these microlocal people can do it. I mean, now that you know that you have this, you could then apply some machinery and try to derive that. So the difficulty is that to apply the machinery, if you don't have these a priori estimates, they're not going to give you a priori estimates just from some expansion. But after you know that things are converging, presumably you can. So maybe it's not crazy. But for this one here, I'm not quite sure. So this one will go to zero at some unclear rate. Yes. Yeah, I didn't write it. So the rates depend on this J. So yes.
Okay, thank you very much.
Yes.
Okay, yeah, first how?
Wonder you have good control of the Ricci away from the singular ones. How about full curvature?
Oh, you mean for curvature away?
Yeah, away.
So yes. So basically, where was it? I think I mentioned. Sorry. So here, right? So for example, So in fact, you can say more. So basically, since you are away, this thing looks extremely similar to the pullback from the base plus 1 over t times the Ricci flat metric on the fiber. And then the Ricci flat metric on the fiber is flat, if and only if it's a torus or finite quotient. So then if that's true, then the Riemann is bounded. And if it's not a torus, you can see exactly it blows up at the rate, what is it, t, I guess, or t squared, depending if you square it. So yeah, you know precisely how they blow up because they really looks like this cylinder. Metric on the base plus 1 over t times the Ricci flat, but non-flat. Yeah.
I assume you also have some derivative.
Yeah. Also with derivative, yes. Also with derivatives, yes. But what we really are missing is anything at the singular fibers. This method does not work at all. Yes.
Okay, yeah, more questions?
Oh, yes.
Derivative CK, C2K, the number K. Yes.
Oh, yes.
The same number.
Yes. So yeah. So this one K, yes. So you start by deciding how many derivatives you want. Actually, it's twice that. Yes.
Oh,
yes.
okay.
Yes. So yeah. This is the same K. Yes, this is the same K, but the speed depends on J. Yes. So somehow, right. I'm cheating a little bit. So you see here, given K, you obtain this gamma J, but they depend on K, right? So if you increase K, the lower gamma J's may change, as I wrote it here, but they change slightly, in fact. So I believe if you want, you could write some gamma J's that do not depend on K. So there's some kind of terms of an actual expansion. But right now, technically speaking, you fix the K and this gamma J do depend on K. And then you have this many derivatives. Yes. So this is needed because we want them to go to C infinity, 0 in CK for all K. Like this stuff here must go to plural theorem. This stuff has to go to 0 in C2K for all K. So yes. So eventually, even these bad terms, they should have a high number of derivatives. Yes. If this was 2J, that would be a big problem. We will be stuck. Yes. Yeah, and the fact that it's 2K is this technical thing about parabolic Holder norms misbehaving for odd number of derivatives. So we need to skip by 2. But luckily, we're able to do that. So.
Okay.
Thank
Thank you. Can the limit current define some foliation and give some information about the vibration itself if there is no vibration?
Yeah. So you would like to say that, yes. So in reality, unfortunately, we don't know that. So just because indeed we don't have any good regularity about omega infinity right now. So to define the kernel is quite complicated. And then even if you could define it, it's not obvious that it's a holomorphic foliation. So even if this omega infinity is smooth, it's unclear if the kernel would be a foliation, at least on open sets where the rank is constant, but it's unclear if the foliation is holomorphic. So those are the two main obstacles, to somehow get some regularity for omega infinity so that you can define the kernel, and then prove that the kernel is holomorphic. In particular, the rank should be constant on a Zariski open set. So these two things are totally unclear right now. But a posteriori, if you believe abundance, yes, certainly this omega infinity would be smooth away from the singular fibers, and it's the pullback from the base, so the kernel are exactly the fibers that you want. Sorry, there's a third obstacle. Even if you do all of that, the third obstacle is to prove that the leaves of that foliation are compact or closed. So that's a major obstacle. So once you have a foliation, to prove that the leaves are closed, it's really the toughest step. So there are basically 3 impossibly hard steps to use this strategy for abundance, but perhaps one can do some progress on some of these steps. Yeah.
Okay, thank you.
Yeah.
Okay. Yeah, more questions? Okay, yeah, if not, let's thank to the speaker again.
Thank you.
Yeah, and also to all the 3 speakers in this morning. Yeah, thank you.
Okay, thank you.
But that's the same. Okay.
No, this one broke, correct? My work is almost.
Yeah.
Okay. So let me start the afternoon sessions. The thinker is Professor Wu from Tsinghua University, and his title is Nearly Optimal Spectral Gaps for Random Hypothetical Surfaces.
Well, okay, thanks for the introduction, and thanks to the organizer for the invitation. I'm all people, and still feel very honored to get this talk to you. All right, so today I'm going to talk about our recent work. Right, so let's start with some basic setting. Okay, actually close time results of G. We have already the completely mathematical constant complexity one. And what I do have is also Laplacian. So from some standard theory, the section of the Laplacian consists of three eigenvalues, which is starts from zero and dimension. And in this talk, we will focus the so-called square gap. So this is the difference between the first two eigenvalues, which is number 1 and 0, or number 0, 0, so which is essentially the first eigenvalue. This is all the part. So okay. So when I studied square gap, this quantity is related to the, for instance, the connectivity of X, the so-called chip equality and the Euclid equality, or the area of the so-called parameter term, and also some area of the rate of mixing flow is currently negative 1. So the question is okay. So how large can this first eigenvalue be, especially when the G is large? And for this kind of question, essentially, we need two kind of things. Right? One is a electric bond. The other one is to show this electric bond is optimal in some sense. Okay, so what is the bond? I mean, the bond comes from Professor Zhen's old theory, almost 50 years ago. Then from the following theory, okay, so he showed that for any closed hypothetical surface of this G, and then the first eigenvalue is always bounded from above as 1/4 plus some universal constant over the lambda square. Over the lambda square. And there is 1/4. Okay, in this talk, there is 1/4 is very important. This 1/4 is also the bonding spectrum of the hyperbolic plane. And actually, we also know that because just by the formula, for closed the area is 2 pi times G minus 1. Yeah, so we know for some kind of manifold, the diameter of any type of surface of G is always larger than or equal to some universal constant technology. So in particular, if the G is close to infinity, the diameter always goes to infinity. Yeah, no matter what kind of surface we are choosing. So okay, so you see, well, if we combine these two things together, you see, so for this error, when the G is close to infinity, this will goes to 0. So we have the following theory, which is due to Huber or Chen. Okay, we consider this quantity. Okay, this is the right. So this is the super of the first eigenvalue of all hyperbolic surface of genus G. Okay, well, this G is the Morgan space of Riemann surface of genus G. So for this quantity, then we consider the mean su. Then the mean su for the quantity is always more than 1/4. The reason is the lambda we are going to.
你稍微换一下麦克风，就这个，换那个，第一个，对吧？
Okay. Okay. So, right. Okay. So this is the theorem due to Hubert and Jen. So another question, okay, is whether this one quarter is optimal. Okay. So if we check Jen's proof, I think this equality can never be obtained because he essentially just compared the geodesic ball of diameter and this this is the whole surface. They're very different for negative curve geometry. So yeah, for this kind of question, so I think right, either we show there are some example which realize this one quarter, or we can show the existence of certain surface which realize this one quarter. Okay, so first, okay, let's see the following example. I think probably number theories are interested in this example. Okay, so we consider the k-level congruent subgroup of SL2Z, so which is defined by this equation. Okay, so this is 2 times 2 integer matrices with determinant 1. Okay, and we know, this gamma k, is a finite index of this SL2Z. So in particular, this is also a discrete subgroup in the group PSL2R. Right? So then we can consider the following quotient. So this quotient is is a hyperbolic plane quotient by this lattice. So we know this is a hyperbolic object. And then I think we can use some basic probably Riemann surface theorem, or or more precisely the Riemann-Hurwitz formula. I think we can compute the genius of this surface and also the number of punctures of this surface, and they are given as follows. So the genius of this surface is given by 1 plus k squared times k minus 6 over 24. Okay, times some. Okay, I mean something. Okay. And the number of punctures, is given by k squared over 2 times this quantity. Here p is taken over all prime divisors of k. So you say, well, if we let the index goes to infinity, then both the genius and also the number of punctures will go to infinity. And moreover, the number of punctures grows like the genius to the two-thirds. Right, so yeah, this is a special sequence of hyperbolic surface, but no compact. Right? Okay, just some cusp hyperbolic surface. So for this special hyperbolic surface, Seilberg proved the following remarkable theorem. Okay, he showed that I think this is already over 60 years ago. Okay, he showed that for this particular sequence of hyperbolic surfaces, no compact. Okay, he can show the first eigenvalue is always larger than or equal to 3 over 16. Okay. Yeah, and in the same paper, he conjectured that this 3 over 16 can be replaced by 1 quarter. So this is also the so-called famous, Seilberg's one quarter eigenvalue conjecture. Yeah, and I think in the past decades, a lot of people, have made an important contribution to this conjecture. Okay, I just list the following several ones. So the first one I think is due to Gabor and Jacob in 1978, 30 years later after the Seilberg's original theorem. Okay, they showed that the inequality in Seilberg's original theorem can be replaced by a strict inequality. So they removed the equality. And 16 years later, Rodlik and Salek, they improved the 3 over 16 to 171 over 784. And I think the best result for this conjecture so far is due to Kim Salek, which is already over 20 years ago. Okay, they show that this 3 over 16 can be improved by 975 over 496. Right? Okay, it's already look close to 1 quarter, right? But mathematically this is still far from 1 quarter. Yeah, and several years ago, this group book Lee Strombergson, they showed that if the index is small in the sense the index is no more than 226, then this conjecture is true. Okay, true. So I think the hard part for this conjecture is if k is large, what happens? Okay, so where do we introduce this example? Well, actually, this example is helpful to study the closed case. I think so. There's a theorem which is due to Buser, and also Buser, Berger, and Doziuk. They apply Seilberg's original 3 over 16 result actually to show the following beautiful inequality. They show that well, for this quantity, you see the super of the first eigenvalue over the homology space. Okay, they can show the mean super is always larger than or equal to 316. I think well, yeah, if we check their proof, the idea of the proof is kind of cute. I mean, the reason is well, for this special sequence of hyperbolic surface in this Seiberg theorem, this is a cusp surface, but the number of punctures you see is even, right? The number of punctures is even, right? You see is even. So well, if this is even, actually this is right. This is this is on the well, this is on the boundary of the Mumford computation of the modular space. So what does it mean? This means actually we can find a sequence of closed hyperbolic surface which will approach to this cusp surface or this Loder surface. And then they show that actually the spread gap along this sequence is going to have one side continuity. And then they just use Seiberg theorem to get this this inequality. Right. This inequality. And I think in the same paper, Busse also conjecture that this low bound can also be replaced by one quarter. Just like Seiberg's one quarter eigenvalue conjecture. And I think at the beginning of this century, Brooks-Markova, they show that actually Seiberg's one quarter eigenvalue conjecture can truly imply Busse's conjecture. We say that the limit of this quantity and the genus goes to infinity is equal to one quarter. So you say, well, this is the limit. This is not the mean soup. But we know from Huber or Zheng, we know the mean soup for this quantity is no more than one quarter. So essentially, we need to show the mean in for this quantity is going to be larger than or equal to one quarter. Yeah, any questions? Now let's keep going. So I think for this question, for this long-standing open, conjecture, it was recently solved by a group from UK. Heidelberg Key. They confirmed this conjecture. They truly show that as the genus goes to infinity, then the super of the first eigenvalue over the whole modular space, the whole modular space, will converge to one quarter. And their proof, sure, they do not firstly solve this Seiberg's one quarter eigenvalue conjecture. Actually, they use something, the so-called random hyperbolic surface. So they use some idea comes from some geometry and the probability. So now, I am going to introduce some random hyperbolic surfaces. Then this is called the three cadence. I mean, just from some people, use this word. The three cadence, is a special Asian time, China, right? And because we have three fancy model random hyperbolic surfaces. So now I'm going to introduce case by case. So I think the first one was introduced by Brooks-Markova over 20 years ago. I think their construction is to glue to an ideal hyperbolic triangle in certain way. I'm going to introduce later. Just we have some a certain model, and the idea is it comes from some so-called oriented three regular graph with two vertices, and then we replace each vertices just by a hyperbolic ideal triangle, and then in certain way, we are going to get a so-called no compact hyperbolic surface SO of gamma O, and also is natural conformal amplification. As I say, what does it mean? This means just by filling in is all of its cusps. So if the genus of SO gamma O is 1, then this SC is not hyperbolic again because it's just torus. So if this SC is still hyperbolic, we need this SO genus is going to be larger than or equal to 2. So for this model, Brooks-Markova, in the paper, they show that actually there exists a universal constant say larger than 0. Such that as the genus goes to infinity, the following probability is equal to 1. So what that means? It means, as the number of vertices goes to infinity, actually almost every hyperbolic surface in this Brooks-Markova model, we have first eigenvalue larger than this universal positive constant. I think this is okay. This is the first result on uniform spread gap of a random surface in literature, and also this constant C is implicit. It's implicit. Okay. So yeah, this is the first order. Okay. Okay, the second model is the so-called Wave-Peterson model. So this is we let MG just be the modular space of all closed hyperboreal surface, all Riemann surface, okay, of genus G. And on this modular space, we have a lot of kind of classic or canonical metrics, and for our case, okay, we just induce this modular space with the so-called Wave-Peterson metric, which is a natural L2 metric in this space. And under this metric, this modular space will have finite volume. So then up to some scaling, right? We can always assume this space is a probability space. So this actually gives a probability measure on the modular space. Yeah, I'm not going to introduce the Wave-Peterson metric in details, but we just assume we have certain good probability measure on the whole modular space. Okay, so for on this space, Mizrahi, I think she is the first person to study the spread gap on this model, and she proved the following beautiful theorem. I think she gave a talk in 2010, the SM talk, and then the paper was finally published in 2013. Okay, she proved the following. She proved as the genus goes to infinity, the following probability is equal to 1. Okay, so what this means as the genus goes to infinity, actually almost every hyperboreal surface of genus G, we always have first eigenvalue larger than 0.0024. This is not full set. Okay, for sure, for arbitrary genus, we can construct some hyperboreal surface, with arbitrary small first eigenvalue. Right, but she proved the following beautiful probability. So another question is, so how to improve this? Improve this low bound, right? This 0.0024. Then just joined with my former student Yu Haoxue. Okay, several years ago. We prove the following. We prove for any epsilon larger than 0. Then as the genus goes to infinity, almost every hyperboreal surface will have first eigenvalue larger than 3 over 16 minus epsilon. And our proof is completely different from Mizrahi's original proof because Mizrahi essentially showed that as the genus goes to infinity, a random closed hyperboreal surface has Cheeger constant larger than around 0.1. And then use Cheeger's inequality. But our proof is use Sepper's choice formula. We take the integral of Sepper's choice formula over the whole modular space. And then get some effective bound, to get this this theorem. And actually soon later, this is also independent proved by Nikolowski and Red. And I think 3 years ago, Al-Sarman and Wong, they improved this 0.16 to 209, by a quite long paper, or 100 pages, I think. But so how to do next? This is still not optimal, right? Our expectation for the low bound is it's going to be 1 quarter because we have a 1 quarter for the up bound. So I think last year I think it's a big deal. Al-Sarman and Wong, they in a series of papers, they improved. Mizrahi's original low bound like 0.024, all this 0.16, to this 1 quarter minus epsilon. And this is optimal, right? Because one quarter plus epsilon is natural up bound. So what does it mean? This roughly speaking, this means as the genus goes to infinity, almost every sequence of hyperboreal surface of genus G will have first eigenvalue tends to 1 quarter. Right? Because 1 quarter plus epsilon is also up bound. And then I think almost 7 months later, this group had the Masiro Thomas. They improve. They reprove Al-Sarman and Wong's the theorem, and also they improve this epsilon to the G to the some negative positive constant. And Yashar remarked that their proof is completely different from Al-Sarman and Wong's original proof. So this is so this is the second model. And so what's the third model? The third model is as follows. It's a so-called covering model. So the setup is first we fix a compact hyperboreal surface. And then we consider all its n covers. Okay, for instance, if we fix n is 100, well, actually it's not how to check. We can only have finite covering surface of this fixed compact hypersurface, of degree 100. Yeah, so this is still a discrete model. Okay, your discrete model. So this also gives a natural, probability measure, on this space, and it's quite algebraic, right? Okay. So now, so for this, random cover, I think also several years ago, McGee, Lord, Puder, they proved the following beautiful theorem. They show that, well, for any epsilon larger than 0, as the number, as the number of the covering degree goes to infinity, actually almost every covering surface, almost every covering surface, so the spectra, intersect with this interval from 0 to 1, 3 over 16 minus epsilon, actually is exactly the same as the spectra of the base surface intersect this interval. So what does this mean? This means, well, as the covering degree goes to infinity, almost every covering surface actually, we have no eigenvalue in this interval. So in particular, well, if the base surface has first eigenvalue larger than 3 over 16, so their theorem tests that as the covering degree goes to infinity, almost every covering surface will also have no eigenvalue. We also have first eigenvalue larger than 3 over 16 minus epsilon. So this is their point. And in the same paper, they conjecture, well, this 3 over 16 can also be replaced by 1/4. So I think last year, McGee, Puder, and Verhander, they truly confirmed this conjecture. They show that their original result 3 over 16 can also be replaced by 1/4. And also, several months ago, still this group, this group of young people, had Cyril Thomas, they improved this epsilon to G to some negative positive constant. But actually see that their proof, had depend on this work, negative Pearson case. I mean, it's it's very different. All right, so now, let's go to the first law model, because for these 3 models, we already know 2 of them already have optimal, right? Almost optimal, nearly as regular. So how about the first law? How about that? So that's let's go back to the first model, which is the Brooks-Markova model. So now, I'm going to introduce a little bit more details on this model. So what is the Brooks-Markova model? Well, first, we start with the standard oriented hyperbolic ideal triangle, with vertices 0, 1, and infinity. So what does this mean? Well, you see, well, this is on the upper half plane. And we have 3 vertices. One is 0, 1, and infinity. And we draw these 3 points just by some hyperbolic line. So we're going to get this ideal triangle. And on this ideal triangle, we have 3 special points, which are so-called middle points. On each line, so which is I plus 1 and 2 and 1 plus I over 2. Why they are special? Actually, if we pick any 2 points of them, then they are on the they are on the same whole sphere. Now, actually, for these three different whole spheres, they are tangent to each other. So on such a hyperbolic ideal triangle, there is a unique triple point, such that each 2 point is going to be right. It's going to be on the on the same whole sphere, and moreover, the whole sphere are tangent to each other. So these 3 points are very special. And then we how to glue 2 oriented hyperbolic ideal triangles. We glue in the following way. So you see, right? We have 2 ideal hyperbolic triangle. Well, we just glue these 2 lines. But probably we can have some sharing, right? Because these are 2 geodesic lines. We can have some sharing. So we also need to glue the 2 middle points of these 2 lines. So we're going to get a hyperbolic idea, quadrilateral. So in the language of technical theory, which means we do not have sharing coordinates on this line. So this is the gluing, the gluing scheme. Okay, and then let's go back to the original construction of Brooks-Markov model. Well, we let the gamma be a 3 regular graph. Okay, and V gamma is the set of vertices. And then we are going to have a orientation on this graph, on this real graph. And the orientation actually is a segment actually for such that for the S vertex, there's a cyclical ordering of the 3 edges. Marked in this this set 3i minus 2, 3i minus 1, 3i. Okay, so for each and each vertex, we are going to have an orientation. And now we just define by by this Fn star, just be the set of all oriented 3 regular graph with 2 vertices. And here gamma is a 3 regular graph and O is the orientation. And so you say just like what we said before. Okay, so for each vertex we replace it by a ideal hyperbolic triangle. Okay, so we're going to get, you see, for each pair gamma O, is going to correspond to a cusp hyperbolic surface, and also we consider its natural conformal communication, which is called SC. And now our main theorem is as follows. So our theorem, says the following. This is joined with Yang Shen. Currently he's a postdoc at Fudan University. We prove the following. We prove for any epsilon larger than 0. And the number of vertices goes to infinity. Actually, a random closed, you see, this is SC, right? A random closed hyperbolic surface in this Brooks-Markov model, it also has first eigenvalue larger than 1 colon minus epsilon. So what this means even for just go back to the first model. The first model also has nearly optimal spread gap. So I think so for this model, it also has nearly optimal spread gap. And I think this is the first improvement on Brooks-Markov's original low bound in the last 20 plus years. Only speaking, I think we try very hard. Try very hard. Also try to get some intermediate result. Like 3/16 also for this model. But I think if we go back to check the proof of this 3/16 result for both of the V-Prism model and the current model, actually I think there are 2 important points. One is the Sepp-Choice formula. The other one is we need some effective bound on closed geodesic of length, uniform comparable to log. But I think for both of these points, it's not easy for us to put this, to put these 2 kind of ideas into this model. So this is why we stuck for quite a long time. But last year, we saw these 2 papers by polynomial method. We just realized, Sepp-Choice formula is it's not necessary. We do not need to use Sepp-Choice formula. And on the other hand, we also do not need to bound the closed geodesic of length, which is uniform comparable to log. We only need to bound some closed geodesic of length, which is uniform bounded from above. Even the constant can be arbitrarily large, but is independent of the genus. So this is why we can get this theorem. And and then we can use something we already obtained for these years, and then together with the polynomial method to finish the proof. Anyway, so now let's roughly describe what is the new ingredients gradients in this proof. So first we give a new description of this Brooks-Markov model. So here's for any n larger than or equal to 1, we assume S6n be the permutation group of 6n elements. And then we consider the following set, which is a subset of S6n times X6n. And the first element is has order 2 for non-fixed point. And the second one has order 3 and also non-fixed point. And this PSL2Z has a nature 2 generators, right? Which looks like one is B, the other one is C. But this B has order 2, this C has order 3. So this is like a free product. But it's not a free group. It's a free product of 2 elliptic elements. And then you see, for each pair sigma tau, actually we can give a unique group homomorphism from PSL2Z to S6. Why? Because this PSL2Z is uniquely generated by B and C. Right? It just totally depends where this B and C send to. Right? So for this group homomorphism, we send B to sigma and we send C to tau. And both B and sigma has order 2, and both C and tau has order 3. And And okay, we just use some fancy language. Actually, this is just means what that means. It just means for any pair in this new model. Actually, this SO sigma 2. We will give a covering surface of the modular surface, which is H quotient by PSL 2Z. And here the covering is no standard topological covering, is some orbifold covering. Yeah. All right, and probably we can see example. So you say, this sigma 1 is order 2, right? No fixed point. Is we send 1 to 6 and 6 1, and we switch 2 and 5 and also 2 and 3. Right? So it's order 2, a fixed point free. And this tau 1 is some orientation. So this sigma 1 corresponds to some 3 regular graph, and tau 1 corresponds to some orientation. And then how do we glue? You say, we have 2 vertices, and each vertex is a ideal hyperbolic triangle. Say 1 and 2. And then you say we glue 1 and 6. You say we glue 1 and 6. Well, if we glue 1 and 6, we're going to get an ideal quadrilateral, right? And then we also glue 2 and 5, and also 3 and 4. So essentially, we just identify your two identical hyperbolic ideal triangle. So we're going to get a hyperbolic 3-punctured sphere. And the second one is you say, the 3 regular graph is the same as and the previous one, but the orientation is different. You see, here is 1, 2, 3, here is 1, 3, 2, and here is also 4, 5, 6. And then so how to glue them? You see, we still glue 1 and 6, right? So we're going to get an ideal quadrilateral. Okay? And then we glue 2 and 5. We say we glue 2 and 5, and also 3 and 4. So we get a torus. Right, we get a torus, but we also need to remove the infinity point. So essentially, we get a hyperbolic 1-punctured torus. Right. So you say, so you see here, if the orientation is different, you see we may get different hyperbolic surface, even they have the same 3 regular graph. Right. Okay. Anyway, so I think so for these 2 models, you see one is from this original Brooks-Markov model. And the other one is is from this new model, right? So actually, it's know how to check for any element in this Brooks-Markov model. This will correspond to some hyperbolic cusp surface in this new model. And we show that in these 2 models, if we consider some geometrical property, you see, we divide some event in these two models. Actually, we can show that for any n larger than or equal to 1, then the probability of these 2 events actually are exactly the same. Even the model are different. So if we would like to show a random surface, in this Brooks-Markov, in the original Brooks-Markov model has a nearly spherical gap, right? So it's sufficient to show a random hyperbolic surface. In this new model, it has a nearly spherical gap. So how to do next? I think this is so actually, the base surface has some 1 to 1 will correspond to certain covering surface of this original modular surface. So I think comparing to the original work of Head and McGee, they essentially consider the covering cusp surface. So I think a major difference is the following. You see, right? For this new model, it still looks like some covering model, but actually they are very different. So you see, if we consider the 6n covering surface of the whole modular surface, actually this Brooks-Markov model actually is the asymptotic measure 0 subset of the whole 6n covering surface. So the original theorem from Head and McGee actually cannot tell us too much things, because this is asymptotic measure 0. And I think so when you define something, I think this is quite technical. You can omit. And if you are interested, I'm happy to answer your question after the talk. But anyway, we are going to use the essential idea or the method. We are going to use the so-called polynomial method developed by Chen, Gazawagas, Trump, and Verhende. And also McGee put Verhende last year. And I think so the essential thing we need to show is to show the we need to show the expectation of certain trace is going to have a very nice polynomial expansion, and moreover the error term will have a reasonable bound. And from this expression, actually, we can explicitly write down what is U0 and U1. And this U1 is very important for us. And so the next one is, okay, we need to show the U1 defined here. Okay, U1 defined here. So to show this U1 has a very nice low bound. So okay, we can do show that for any step adjoint alpha in this algebra. Then the mean suit for this U1 of R to the P, and have the value to the 1 over P is going to be lower than law of some other operator. Okay, so these are the essential two different things. Right. And then I think, okay, well, if we have these two theorems, and then we just compare the work of McGee, Pullover-Handel, and also the formal work of Handel and McGee, yeah, we can prove the following limit. Yeah, we can prove it. So the following limit says that, well, and you say, and the number of vertices goes to infinity, then the following probability is equal to 1. I mean, converge to 1. Okay, so what does this mean? This means, well, and the number of vertices goes to infinity. Actually, the spectra, you say, okay, the spectra, right, of this Brooks-Markov model intersect this interval from 0 to 1 quarter minus epsilon is the same as the spectrum of the original surface intersected with this interval from 0 to 1 quarter minus epsilon. Okay, and now, well, actually, we already know the first eigenvalue of the base surface, the first eigenvalue of the merged surface actually is strictly larger than 1 quarter. Actually, I think it's like 20, it's over 20. So this in particular tells us, you see, the spectrum of this guy intersect this interval is empty, right? It's empty. Okay, yeah, well, yeah, if this is empty, so this means this is also empty. So what does it mean? This means as the number of vertices goes to infinity, yeah, a random Brooks-Markov model, yeah, will have no eigenvalue between 0 and 1 quarter minus epsilon. So which means the spread gap is larger than 1 quarter minus epsilon. Okay, and then we finish the proof. But this theorem is only for SO. You say it's for open case, right? It's for open. And our theorem is stated for compact case. It's for compact case. So how to transfer from open, from open to closed? So we also need the following additional queued proposition. The proof is not that hard. It's just, I think if you check the proof, essentially we just apply the Schwarz PK lemma. And okay, we show the following. Okay, we show, well, if SO is a cusp hypersurface, okay, with genius larger than or equal to 2. And we also let SCP is natural conformal complication just by filling all its cusps. Then we can show, you see, the first eigenvalue of the compact case is always strictly larger than the real quotient of the open case. And yeah, we already show, right, for the Brooks-Markov model, a random cusp hypersurface already have spread gap larger than 1 quarter minus epsilon. And then, okay, we just use the inequality, right, to get the closed case. Yeah, the closed case. Right. So you see, even for the closed case, yeah, so we can get it for a random closed hypersurface. It also has a spread gap larger than 1 quarter minus epsilon. So this will finish the proof. Right. I think I have 5 minutes. 10 minutes. Oh, okay, I'm going to stop earlier. Okay, so for this proposition, I think even the proof is easy. I think well, okay, we will see. Yeah, okay, it links two interesting fundamental questions. So, and Adam will talk. So please let me introduce that two fundamental questions. Okay, so actually we have two fundamental questions. So okay, the first one, okay, is the following. Actually, well, for a complete cusp or no compact hypersurface, okay, or finite area, actually the spectrum of such surface actually consider several parts. Yeah, one is 0. 0 is always the eigenvalue. The reason is because the surface has finite area. So constant function is always the eigenfunction. And also this interval from 1 quarter to infinity. Okay, this is comes from the continuous part. Yeah, because it's no compact. And also some possible non-zero eigenvalues. Okay. And actually, yeah, well, there's I think this is probably the older thing. Okay, it's older question. Probably go back to 1980s. But you can also see this question in Salik's survey. Okay, the question asks that, well, for any complete low compact hypersurface of an area, yeah, does it always has a non-zero eigenvalue? So this is still valid open. Yeah, I think the expectation is no. So what this means? This means there should exist certain cusp hypersurface such that it has no eigenvalue except 0. Okay. But we do not know the example. And the other one is, okay, and okay, for this question, actually, well, yeah, if we use early theorem of Yang Yao, Professor Yao, and also Zograf, I think this is essentially due to Yang Yao, right? Okay, Yang Yao proved the theorem for closed case, but Zograf, yeah, okay, just realized, or Yang Yao's proof also works for finite volume case. Okay, so they show that actually for a finite area hypothetical surface, then the real quotient of this finite area hypothetical surface, okay, is going to be no more than 4 times g plus 1 over 2g plus minus 4. Sorry, minus 2. So what does this tell us? You say, well, if the number of punctures, is significantly larger than the genus of the surface. So you say, for instance, okay, if n is larger than or equal to 14g plus 18, then this real quotient, okay, is going to be no more than 1/4. Well, yeah, if the real quotient is no more than 1/4, then we can use some standard spectral theory to detect a non-zero eigenvalue because this spectral is below the continuous path. So I think, well, if we were to find some common example, I think, yeah, we need the number of cusps, okay, is going to be slow. Okay, sorry, it's going to be small, okay, comparing to the genus. Okay, and the other one is, I think this is I don't know who asked this question at the beginning, so I call this folklore. Okay, so the question asked that for all genus larger than or equal to 2, so does there exist a closed hypothetical surface of genus G? Yeah, sorry, that the first eigenvalue is strictly larger than 1/4. Probably, yeah, okay. Well, yeah, we can also see the following statements from a survey by Raymond Wehander last year. Okay, he wrote, okay, in the setting of hypothetical surfaces, the analogous or revoluting property that of a hypothetical surface with first eigenvalue larger than or equal to 1/4, this is equivalent to the validity of the Riemann hypothesis for its Zeta function. And no such surface has yet been proved to exist. So actually, well, if the genus is is small, actually we already know the existence of such surfaces. Okay, but I think the problem is hard when the genus is large. Okay, so why I introduced this question? Okay, the reason is the following. You see, well, if we use the comparison before, actually, okay, we're going to have the following proposition. So, okay, will SO be a cusp hypothetical surface, right, with genus larger than or equal to 2? Yeah, such that its conformal quantification, yeah, has first eigenvalue no more than 1/4. Then our conclusion is, okay, this cusp, this original cusp hypothetical surface, will always has a non-zero eigenvalue. Yeah, why? You say, yeah, why is it true? You say, well, right? You say, well, right? You say, yeah, if the compact, you say the compact case has first eigenvalue no more than 1/4. In quality, okay, this tells us the real quotient of the original cusp case, yeah, it's going to be strictly less than 1/4. So which means this is below the continuous path. Okay, so then we can use this standard spectral theory to detect a non-zero eigenvalue. Okay. So okay, so this is I think this is right. This is a okay, this is a remark to start like this question. And the second one is the following. You see, well, yeah, this is X gamma K is the surface inside because 1/4 eigenvalue conjecture. Okay, and we already know, right? Somebody already show, some group already show, when the index is between 1 and 226, then this special hypothetical surface will have a first eigenvalue larger than or equal to 1/4. Okay, and then okay, we can say that is a conformal quantification. Right. Then okay, if we use this inequality, because this inequality tells us that the compact case will have large first eigenvalue. Okay, so this in particular tells us that you see the first eigenvalue of this I think 220 right surfaces, yeah, closed hypothetical surfaces, yeah, we have first eigenvalue yeah, strictly larger than 1/4. Okay. So yeah, we have right. Okay, so why I read this case from 7 to 226, because if case between 1 and 6, you can easily check from the formula. The genus is always 1 or 0. So which, and if we make a computation, yeah, this will not give us hypothetical surface. So we need this index larger than or equal to 7. Okay, so okay, I think yeah, I'm going to stop here. Yeah, thanks very much for your listening.
Thank you very much for the talk. Are there any questions?
Maybe I could ask a little question about possible so you only consider metrics of constant curvature.
Yes.
But what if you allow a little bit changing of
Oh, I see.
curvature?
Yeah, that's right. Okay, I think if we allow the surface as a variable curvature, right? I think for this proximal curve model, I think it's hard to formally establish. But for the current model, we can still consider this case. I think probably due to Borman and his causes. Okay, they can show that if we fix a base surface with variable curvature, probably negative. I think they can still show a random curve where has some spread gap, which is larger than the universal curve spotting spectrum. I'm something like that.
Yeah.
Right.
Indeed. Okay, maybe I can ask one more question.
Sure.
So you talked about this gap between 0 and 1/4.
Yes.
Are there any concrete examples with something in
between
between?
0 and 1/4?
Yes.
Yeah, that's very hard. I mean, if the gene is large, I think we do not have any example. Yeah, because we only have this step because one called eigenvalue conjecture, but we do not have explicit example. But for low genus, yes, we have. You see, for low genus,
low genus, yes.
Yeah, that's right. You see, right, just like k from 7 to 2. Right.
Yes, low genus you can do.
Yeah, that's right.
Okay. All right, thank you.
Jones? Okay, so thank you for speaking again.
Okay, thank you.
So we start at 2:50 in the floor. Okay, so our next speaker is Professor Binlong Shen from Sanyet University, and he will talk on the construction of maximal foliations in general relativity. Thank you.
Thank you, Professor Skaya. It's my great pleasure to speak for this conference. To begin with, let me mention, because this talk has been given yesterday in Shanghai. So if you have heard of this lecture, I apologize for that. Today I'm going to talk about some result in Lorentzian geometry and Einstein equations. This talk consists of two parts. In the first part, I will talk about some result done by myself earlier. And in the second part, I will discuss my recent joint work with my current PhD student, Ruobing Wu. So let's start. Let's begin with a theorem Liouville type. It says the following. Suppose we have a 4-dimensional geodesic complete space-time, which is just a Lorentzian manifold, satisfying the following two conditions. One says if the space-time admits a time-lag Killing field, so the time lag means the norm of the vector field is strictly negative everywhere. Killing means the lead derivative of the metric is 0 with respect to this vector field X. The second condition is just said the space-time is vacuum. So the ridge curvature is identical to 0. The conclusion is the space-time is flat. That means the remaining curvature tensor of the Lorentzian metric is identically equal to 0 everywhere. So this theorem is a kind of Liouville type theorem. So let me remind you all these 3 important conditions, actually maybe 4 conditions. The first one is dimension is 4. The second is the space-time geodesic complete, and the time-lag Killing field and the vacuum. So as far as we know, all the explicit examples of Einstein equation, vacuum Einstein equation, we constructed. Almost all these examples contain singularities or black holes. So this phenomena is not accidental. So if you put all these conditions together, like geodesic completeness, or time-lag Killing field, or a vacuum condition together, then the space-time is flat. So no curvature at all. Let me mention a remark. So if the dimension is strict greater than 4, then result does not hold. A simple counterexample is as follows. So you take a complete ridge flat and a non-flat remaining manifold dimension greater or equal to 4. You just time this manifold with time. Put a minus sign, put a cross product metric here, then you get a ridge flat space-time complete, geodesic complete, but it's not flat. And we also have a time-lag Killing field, DDT here, just DDT. It is killing for obvious reason. So that means the dimension restriction cannot be dropped. So you here in the previous theorem, four dimension, we require the dimension of the space-time is just 4. The usual dimension of the space-time. This is a little bit history. Probably the first researcher in this direction are Einstein himself and Pauli. But I will not mention here. The most recent is Lichinovic in 1955. Yeah, he proved the result under some conditions, two conditions, asymptotic flat and the chronological condition. Asymptotic flat is a condition imposed on the 3-dimensional manifold. And the chronological condition means the space-time does not contain time-lag closed curves. Chronological condition here was used to reduce the space-time somehow to 3 dimensions. So if the space-time is satisfy chronological condition, then we can just work on a 3-dimensional manifold. So this is the reason why they use the chronological condition and the asymptotic flatness. Michael Anderson make a big progress in this direction. He removed the asymptotic flatness, but still assume the chronological condition. So somehow these people are just worked in 3-dimensional manifolds, not 4-dimensional manifolds. But actually, here the main observation is that this theorem we can have a purely local estimate, curvature estimate. It has nothing to do with the topological condition or some causal conditions at all. So let me give a few terminologies here or notations here. So we have triplet, M bar, G bar, X. M bar is a 4D Lorentzian manifold. G bar is a Lorentzian metric. X is a time-like vector field. Here, it is not necessary to be killing the time-like vector field. X lower star is just a covector field due to X. It can be defined in a very natural way, induced by this X and the Lorentzian metric G bar. Based on these two guys, G bar and X, then we can construct a Riemannian metric, very natural way. G hat, we call this G hat. So we also use the notation B hat X0A to indicate a geodesic bore with respect to the Riemannian metric G hat. So this notation here means compactly contained in the manifold. It simply says the closure of this bore, geodesic bore, is also compactly contained in M bar. Oh, this is the estimate I mentioned previously. So if the Ricci curvature is identical to 0 on the geodesic bore, this bore is defined by using the Riemannian metric associated with the Lorentzian metric and the time-like killing field. So this is a killing condition. So vacuum killing, if these two conditions hold in the geodesic bore radius A, then we have a curvature estimate here. So the curvature on the bore radius A/2, then the supremum of the curvature is bounded by A to the power 2, -2. Here the constant C is an absolute constant. It depends on the dimension, but dimension is 4, so the constant is just a universal constant. So this is a purely local result. It has nothing to do with the asymptotic flatness, the causal structure, nothing. It is a purely local result. So this is the reason why the previous theorem holds true without asymptotic flatness or causal condition. So the following theorem is a generalization of the previous result. So you can perturb the vacuum condition a little bit and perturb the killing condition a little bit. So it is the following. So the first one says if the Ricci curvature, let me see, if the Ricci curvature and the Lie derivative and the covariant derivative of the Ricci curvature, the Ricci curvature is defined by the Lorentzian metric, and the norm is measured by the Riemannian metric. If these two guys are bounded, and the Lie derivative are also bounded, I mean up to second covariant derivatives. This is a scaling invariant statement. This statement is invariant under scaling. Then we have curvature estimate. It's just the same estimate as before. So if the space-time is is vacuum, then reach is identical to 0. So the first condition holds automatically. And the second, if the vector field X is killing, then the lead derivative vanishes. So the second condition also hold automatically for any A, actually, for any A. So under the condition of the theorem, the reach is identical to 0, lead derivative identical to 0, then we can take A goes to infinity, then the Riemann curvature tensor is identical to 0, But you have to prove that if the space-time is complete with respect to the Lorentz metric, then it is also complete with respect to the remaining metric. So this has to be proved. We can prove this. Okay. So this theorem. The third theorem is the following. It also motivated by the first theorem. So it is a little bit stronger. So we just assume the Ricci curvature of the Lorentz metric is bounded, and the lead derivative is bounded without higher covariant derivative bound. Just the boundedness of Ricci curvature and the lead derivative. Then the result is the following. So for any epsilon, positive epsilon, and Q greater than 4, there are some constants on the immersion map. This psi is just an immersion. Immersion means it is a differentiable map so that the differential is non-degenerate everywhere. From ball of radius almost A to the manifold, then we can pull back the Lorentz metric G bar and denote this guy by the same notation, G bar. This G bar is also metric, Lorentz metric on a ball over Euclidean space R4. So it satisfies the following three conditions. The first one says this map is not this map covers a relatively large region, not a small region. It covers almost a ball radius A. The C2 is a constant depending only on epsilon and Q, epsilon and Q, almost universal. The second just says the coordinate function harmonic with respect to the remaining metric, G hat remaining metric. Here, this X is not killing anymore. It is just a time-lag vector field, time-lag vector field. And the third condition roughly said, the first one in the third condition roughly says the metric is close to a Minkowski metric. It has signature -1, +1, +1 in the diagonal form. The off-diagonal form entry are zeros. All these are zeros. So third, the second it just says the Lorentz metric, the W1Q norm is bounded in scaling invariant form. So this theorem, roughly, this theorem says if you assume the lead derivative is bounded, if you assume that the Ricci curvature is identical to 0, I mean, if the space-time is vacuum, if you have a time-lag vector field so that the lead derivative is bounded, then we have W1Q estimate or W1P estimate for any P, Here, the big difference with many results in remaining geometry is the following. We do not assume the space-time is not collapsed on this board, if radius A. We know no non-collapsing condition here. It is possible that this map to be not to be one-to-one, it's just some covering map. So let me, okay. Maybe I skip this part. This is the second part of my talk. As I said before, it is some joint work with my my student, Robin Wu. Yeah, in general relativity, there is a famous L2 boundary curvature conjecture. This conjecture was proposed by Kleinman, Sergei Kleinman in 1999. It simply says the following. It is about the well-posedness of Einstein equation. It is about a well-posedness of vacuum Einstein equation. The well-posedness just says the following question. So what kind of initial condition can be imposed on the Cauchy surface so that the vacuum Einstein equation can be solved? Kleinman's conjecture states that we can only impose a bounded curvature, space-time curvature, then the Einstein equation can be solved, always can be solved. So this is a very elegant conjecture, but yeah, they said they have solved this conjecture after many groundbreaking works. But their proof depends on the maximal foliation, and the maximal foliation played a very crucial role in their proof. Right? Maximal foliation means it is a foliation, consists of maximal hypersurfaces. Maximal hypersurface, just like a minimal surface in Riemannian geometry. Yeah, it just means the surface satisfy mean curvature equal to 0 condition, mean curvature 0. The second I want to say is about the global stability of mean curvature spacetime. This work was also done by Kleinman. Yeah, he joined with Cristodolo. So in their proof, they also used maximal foliations. This is a very important condition in their proof. So they only proved the global stability under the existence of maximal foliation. So some smallness of the initial data, but they require this small initial data maximal, also maximal. So yeah, this is the definition of explanation of maximal foliation. That means there exists a timeline function tau such that all level sets of tau are maximal hypersurfaces. This is a kind of a gauge condition, because the Einstein equation is an equation about tensors, So the tensor equation, somehow, if you write the equation in bad coordinates, then they will behave bad. If you write it there, that equation in good coordinates, then the equation will behave well. So we need to find a good condition. So the maximal foliation is a good coordinate, at least one coordinate function, good one coordinate function. So it's kind of a gauge condition. But this the Euro approach to the construction maximum foliation here encountered fundamental difficulties in solving Cauchy problem, because for the L2 boundary curvature conjecture is an evolution problem. You start with a Cauchy surface, then you ask whether there exists a there exists a solution for the question. So we don't know whether the existence of a maximal surface, right? So in this problem, if you start just arbitrary initial data, just with bounded L2 curvature, which is not a maximal, not maximal. So how to prove the bounded curvature conjecture, L2 bounded curvature conjecture? This is a problem. It's a problem. Yeah. So I joined with my current PhD student. We proved the following theorem. This paper had not published yet. It just finished. This theorem is the following. If we have a three-dimensional manifold M0, GH, this triplet, the asymptotic flat initial data set, satisfying vacuum constraining equation, And the following several conditions, I will not explain. I will not explain all these conditions together. I will not. It roughly just says, the mean curvature has to be small. All this condition is about the smallness of the mean curvature. You see here, this is the LP norm of the mean curvature times something less than epsilon 0. Epsilon 0 is a constant depending on somehow is a universal constant. E1, E2, E1 you can think of E1 as a L2 norm of the curvature. Here, because the space-time is not a maximum, so we have to add the L4 norm of the second fundamental form. E2 is the covariant derivative of the curvature, and plus some rest term consists of the second fundamental form. So all these conditions is a bit ugly, but it can be replaced by some other form. But still, they are all these conditions about the smallness of mean curvature. This is about mean curvature itself, about the derivative or covariant derivative of the mean curvature. Yeah, this condition, you can think of this condition as the smallness of mean curvature condition. Yeah, if this condition, if the previous condition are fulfilled, then there is a space-time m bar g bar. Yeah, and the time function tau. The level set of tau forms the maximal foliation. Yeah, the most importantly, this foliation covers the initial hypersurface. So you can replace the initial hypersurface by a maximal hypersurface or by a maximal foliation. So that is the theorem, the consequence of the theorem. Yeah. So let me talk about a little bit about proof, the idea, only about the idea. Yeah, this paper is a little long, so I only talk about the idea of the proof. The key point is you have to prove the existence of one maximal hypersurface, right? So the purpose is to prove the existence of a maximal foliation covering the initial hypersurface. So you have at least you have to prove the existence of one spatial hypersurface maximal. So the idea is to use mean curvature flow. But here there is some new feature. No background manifold. No background manifold. We want to use mean curvature flow to deform the initial hypersurface so that they will evolve to a maximal hypersurface, but no background manifold at all. This is a new feature, and it differs from the previous situation in all previous results in Riemann geometry. So our strategy is the following. So we, first of all, you solve the Cauchy problem for vacuum Einstein equation for a short time. You solve the Cauchy problem. Then this will give rise to you a space-time, 4-dimensional space-time. You can take this as a background, M bar 1, M bar 1. The second step is to solve the mean curvature flow within this this background, M1 bar, M1 bar. So we have two situations, two cases. In the first case, if the solution of mean curvature flow remains in M bar 1 for all time, then you can just try to take a convergent limit as t goes to infinity. This ideal case, right? So the limit is supposed to be a maximal surface. It's just a rough idea. So for most of the cases, you have the second. So there is a finite time t bar. So as t goes to t bar, t1 bar, the solution approaches the boundary of M1 bar. So in this case, you can take the limit as t goes to the critical time t1 bar as an initial data. Then you still repeat step 1 and 2. So solve the Cauchy problem for this initial data. Then you get a little bit bigger the space-time. Then solve mean curvature flow within the this larger space-time. Then you do the previous steps. Of course, the aim is to prove the above procedure must stop in finite number steps. Must stop. So you cannot do it for infinite many times. So after finite number steps, you have to prove that the mean curvature flow must converge in one coordinate chart or in the final step, it will converge to a maximal hypersurface. Of course, there are a lot of priori estimate has to be done. You have to prove the convergence. You have to many work to do. But the idea just the previous statement. Maybe I stopped earlier. Yeah, thank you.
Thank you very much. Any questions? Okay, so thank you.
Thank you very much.
The next talk will be as scheduled, 3:45. Okay, so fourth talk of this afternoon is by Professor Xiaochun Long from University of Bluetooth. He will talk collapsed manifolds of local boundary covering geometry.
Okay, thank you. Thank you. It's really honor to speak at this conference. Thank you for the invitation. So today I'll talk about a problem in Riemannian geometry where a special class manifold, it's called collapse, means you take each point, take a unit ball, measure the volume. The volume is very small. Then a constant, absolute, everywhere. So we call collapse. But collapse very complicated. So you need to put additional condition help you to understand the structure. So what is the additional condition? You take a ball, unit ball, it's a very small volume, but you take the ball out, the manifold, look the incomplete universal covering space. Then look the which is not collapsed, either the volume of the unit ball on the local universal covering is not small, or a stronger condition. Not only a volume not small, and more or less it's close to a Euclidean ball in some sense. So that's what we call bounded local covering geometry, local bounded covering geometry. Okay, yeah, we just said what I said. And if you put a strong condition, curvature bound, right, section curvature bound, absolute value, normalized, then the structure, geometric and topological structure underlying manifold is well understood by the work of Chigger, Foucault, Gromov, and several others, which has found many applications. So in this talk, we'll report ongoing investigations on a collapsed manifold, satisfying weak curvature condition, either section curvature bound below or Ricci curvature bound below normalized, but plus this condition, local bounded covering geometry. I'll explain why this condition is important or is crucial to understand collapsing structure. Our goal is to somehow partially extend the previous collapsing theory, in particular existence of so-called singular nilpotent structure found on collapsed manifold with bounded section curvature. We try to extend this. Okay, so that's a three-part. Actually, I when prepared this, I take off the proof part. So because the time constraint. Okay, background. So core issue in Riemannian geometry is given complete Riemannian manifold, you understand the geometric invariants interplay with the underlying topology. The regularity of the metric, right? The derivative of the metric, like second derivative, second curvature, or Ricci curvature, or scalar curvature, it's related to complexity underlying a topology of the manifold. Let's start with a very simple one, where section curvature is constant h, any derivative is 0. And we know that by the work Cartan, we have three models. If it's simply connected, then Euclidean sphere, hyperbolic space, if normalized h. Now, what about the weak regularity, right? The trace of the curvature tensor, the Ricci curvature, even simply connected, right? It's a structure be very complicated, even in dimension 4, right? we know in this conference, a lot of speakers talk about Kähler-Einstein, right? Calabi-Yau manifold. That even that class, we still have a lot of questions to understand the topology. Once you understand the constant case, next thing you go to pinching. If the second curvature very close to a constant, what you can say, right? That means if the manifold has the same topology, is manifold does the manifold admit symmetric constant curvature, second curvature, right? Same topology or topological stable. If not, you ask if I can understand all the possible topologies. If not, then you ask even weaker, some topological constraints. So the sphere theorem, Coulter pinching sphere theorem. Homomorphic type is much earlier than the diffeomorphic sphere theorem is by Brundle Shen. And the consequence is, right, that the differential is a diffeomorphic to standard sphere. Now, what about pinching zero? What about pinching zero? Means absolute value, second curvature is very small. But any compact manifold, by rescaling, you can always make section curvature as close to zero as possible. So you have to put constraint, not scaling. You put diameter equal to 1. Then that's Gromov's almost flat manifold theory. It gave a classification. Says this manifold is diffeomorphic to a so-called infra-new manifold, i.e., you have simply connected a nilpotent Lie group and modulo by a group in affine transformations where the translation part is a major part. So like a Bieberbach type theory. Now, what about -1? -1, even arbitrary pinching, the topology is drastically different. So that's work Varma Thurston. There are no pinching stability. There are no classification. So they're very complicated. So in this talk, it's a basic notion is a Gromov-Hausdorff convergence. Let me just quickly review, apologize for the simple thing. So if you have two locally compact matrix space, you can measure the descent structure to two matrix spaces using a map which may not be isometry. It's called epsilon isometry, distort distance, the most epsilon, and epsilon onto all the image is epsilon dense. Very weak measurement. Then you take all the possibilities, maps, which satisfy, you take the smallest epsilon in film, right? You call this is a Gromov-Hausdorff distance. So if you have two space, if a compact space, give any epsilon, you can have a discrete so-called epsilon net, finite many point where they are epsilon separated. They are epsilon dense. I mean, then if you have two finite set match up, then the Gromov-Hausdorff distance is close. So it's very, we can imagine one could be a finite set, one could be a higher dimension. So it's very, very weak measurement. So when we say two space Gromov-Hausdorff close, it doesn't mean anything. It just means, right? If any scale up bigger than epsilon, then smaller than epsilon, then nothing you can say. It's in general. But Gromov proved that. And if you have sequence Ricci bound below, and then there is subsequence always convert in this Gromov-Hausdorff distance. He proved a pre-compactness. And there are two situations. One is non-collapse. If you pick a reference point, if volume uniform bound below, you call it non-collapsing. Otherwise, just one point go to zero, called collapsing, because if one point volume go to zero, give another point, distance finite, that volume also go to there. So actually, so that's, so once you have this provide a fundamental platform. When you study an individual geometry topology interplays, you can use the compactors, the tool. So you study the limit space geometry topology interplay. Once you understand that, you get back to the sequence. So that's how this is being used. Next, we consider non-collapsing. It's easy. Sorry, I shouldn't say easy. It's well understood in most cases. And so non-collapsing, you consider sequence remaining fixed dimension, Gromov-Hausdorff converge. If you assume non-collapsing, here we assume the diameter uniform bounded, we call it, we consider. Then the volume has a lower bound, not just one ball. You can assume this. And this condition, the classical result is central curvature bound in absolute value. Then you can show that when I large, the manifold all diffeomorphic to the limit space. And you can have a diffeomorphism such as the pullback metric, a similar convergence. Now, if you weaker the curvature restriction, -1, then you can have homomorphic, no collapsing. But the regularity is not ideal. It's just Gromov-Hausdorff approximation and homomorphic. And yeah, so people want to show this. There is some a Lipschitz map, but so far no progress. Now, if you further weaker the condition, Ricci bound below, and non-collapsing condition is no longer strong enough, but here you assume the pond is so-called Raffenberger pond. I explained the Raffenberger pond. Then you can get diffeomorphic pullback metric by Holder converge. So Raffenberger pond is basically you fix a delta usually depends on n, small enough, that's enough. A rho is fixed constant. A pond in manifold is called the delta Raffenberger pond. Basically, the consequence is the rho ball is diffeomorphic and biholder close to Euclidean ball. So that's the consequence. The condition is this. It's basically you take any ice between 0 and rho, then you measure the ice ball Hausdorff distance, right? If ice surface small, obvious, the Hausdorff distance go to small. But in the scale S, the small error is delta. If you put ice there, that means you take a pond, you enlarge the ball, rescaling, then you look compared to Euclidean ball. It's not Euclidean ball, but error never get worse. It's delta. So that's a delta Raffenberger pond. That's diffeomorphic beholder. Yeah. Now, once we understand no collapsing, we back to collapsing. I already say collapsing, the pinching theorem. Let me just repeat this. It's called old flat. You fix a dimension, you assume section curvature bound and diameter bound small by a constant, only dependent on dimension. Right. This is a pinching around section curvature. Oh, okay. By scaling, it could be diameter equal to 1, pinching around there. And in this case, you have this nilpotent manifold. We already stated, And this is a cornerstone in the collapsing theory. And an important result in this basic result is this. If you consider sequence collapsing, but bounded diameter, not go to 0, then you actually have this community diagram. So the manifold converge to a, in general, singular space. Now, what you can say is, it's observed by Fukaya that on the frame bundle, right? You have frame bundle, you can have a canonical metric using the Levi-Shaped connection. And assuming then you can have a Gromov-Hausdorff convergence. If a Gromov-Hausdorff convergence has certain symmetry, then the symmetry pass along to the limit. And then miraculously, the limit is manifold. It's not downstairs. Using this, it's a sigma alpha manifold. Then Fukaya, right? He has a fibration theorem when the limit is smooth, but can apply to the limit is singular. That's the key point. And there are some regularities about the fibration band. So when the manifold, both section curvature bound collapsing to a limit, then you can have a map, right? The map leading to the frame bundle is fiber bundle, and it's always invariant fiber bundle. But each fiber in the frame bundle is not infra-new manifold, it's new manifold, and struct group is affine. And there are some irregularities. Okay. So singular nilpotent structure play a role in the, applying collapsing structures to understand some problem in Riemannian geometry. Let me, okay. So here is more, so if the fundamental group is finite, if you have a singular fibration, then the universal cover admits a nilpotent group action, which preserved by the fundamental group. So that's roughly the structure. And then you can use that to prove some collapsing stability theorem. Namely, if you have a sequence collapse under the same condition previously, but you add additional constraint, the manifold too connected. Fundamental is trivial. Second homotopy group is trivial. Then you can show that I large, that the sequence is diffeomorphic stable. Diffeomorphic stable. This the starting point proves theorem using the singular fibration. Another one is you ask a natural question, right? If you have the collapsing sequence and the same condition, and what class, special class, you can always know the limit is manifold, not a singular space. So aspherical manifold is the class. If each one, aspherical manifold, basically universal carving space is contractible. And then if it's called AS type, so there's some technique definition, but I just say, for example, if it's a torus, then it's AS type. If it's a nilpotent manifold, then it's AS type. But flat manifold, not torus, is not, do not satisfy this. And new manifold, compact new manifold times any compact hyperbolic manifold, they all satisfy this condition. So then the limit is a manifold, even it's lower dimension, in general singular space, the conclusion is manifold. And also the same type. Its universal cover is contractible and satisfies the same type condition. And Fukaya, 88, proved this for orbifold type. If you have sequence which orbifold, limit is orbifold. In the proof using the condition where universal is not collapsed. That's for aspherical manifold. This is without Gromov. Okay. Now, once you have both understand that when they have collapsing section curvature bound, then next you want to say, what about section curvature bound below or Ricci curvature bound below? What you can say. Now let's first jump to the Ricci bound below. Unfortunately, the collapsing in general is very complicated, very complicated. So abstractions, first, what is known if you have collapsing sequence is Ricci bound below. First, you know that limit space is a locally compact length matrix space, but its isometry group is the Lie group. That's without coding label. And secondly, there is a Magula slam, actually that's behind almost flat manifold, more general Magula lemma, which says you have manifold, you take a point, you take a small loop, geodesic loop, it's very short because of collapse, you have such loop. Then this short geodesic loop generates in a fundamental subgroup, which is so-called almost nilpotent. So that's the theorem says. You have a short, depending on how short, depending on the dimension. Then in the unit ball, the image, or you can think of in the image entire universal, entire manifold, right? Is nilpotent. That's geometric constraints on the limit space. The second one is not long ago. It's a semi-simply connected. If we think locally simply connected, semi-local simply connected means simply connected means you have a point, you have a ball where any loop is homotopy trio in the ball, right? So you have such a small ball. But semi-local simply connected means you're not contractible in the ball, but slightly larger the size is contractible. In particular, in the universal, that basically means this. But this is our only known result, collapsing with general result, collapsing with Ricci bound below, with bound diameter. Now, what about other things, right? It turned out to be recently examples, various examples have been discovered showing the complexity in general. First, their Pan way, they show that the Hausdorff dimension matrix space is not integer, compact or no compact limit. Secondly, these people say the X contains no topological point. Their limit space, to take any ball, it's not homomorphic to Euclidean ball. There are no such point. So it's locally very complicated. And once we have this in mind, then obvious, you want to study collapsing and the Ricci bound below, obvious is you want to find a smaller class where you can get a meaningful result. Now, what is proper conditions? That's a condition I call local bounded common geometry. First, recall that in Riemannian geometry, when you have section curvature bounded below, if this is 0, lower bound is 0, then all bounded below, you have many remarkable result, like a Betti number estimate for compact manifold, and like a Searle theorem, Searle structures, or if the curvature, section curvature, non-negative, complete open, or the generator's fundamental group over manifold is uniform bounded, corresponding to Ricci curvature. That's a mu-no conjecture. But all these are false with Ricci curvature without any additional restriction. Then what is local bounded common geometry? It depends on what condition, curvature condition. If a Ricci curvature condition, lower bound below, as I said earlier, right? You take it's like an extension of Ramberg point. If the point, the point on the manifold, which unit ball very collapse or lobe very collapse, very small. But you look the ball universal cover, you look the central point, right? Projection point. If that is not collapsed and also locally like biholder to Euclidean ball. So that's concept we call local rewinding Ramberg point. Local rewinding Ramberg point. Another one is for section curvature, you can weaker this assumption, collapsing assumption to local rewinding volume point, means the same size ball on a local universal cover has a lower bound. So every point, so that's the condition imposed. So first, obvious, this condition imply this. Local rebounding Rambler point imply local rebounding volume point, right? And for section curvature less than 1, they are actually the stronger condition hold. That's it's not trivial to prove, but it's a fact. It's a local actually local carbon universal carbon the injectivity readers has a lower one. Now, once we have the condition, the next thing is what do we need a condition for, right? So we try to say under that condition, collapse Ricci bound below and local Rambler point, collapse with section rebound below, local rebounding volume point, you should have the similar feature like singular fibrations we see earlier. Yeah, that's a conjecture. And I want to point out their examples show that this conjecture is false if you weaken these conditions. For instance, if you replace local Rambler point by local rebounding volume point, then it's false. Even no collapse, you cannot have this. And what's the purpose you want to establish this? Because once you have this conjecture, then almost result obtained and the section bound both sides can be extended to this class. Oh, it's not what I said. Okay, actually, I think this is it's not what I said. Should holds, not which false, should holds. I'm sorry. Oh. Okay, under the condition. Now, what's the best way to do this, right? If you metric, you don't have a good regularity, only Ricci bound below or local Rambler point. Now, what's the natural way, right? Natural by smoothing in Riemannian geometry. One important tool is smoothing. Now, let's recall Hamilton's, right? Any compact manifold, you solve this equation, you get a solution, short-term solution, as it's called Ricci flow. And the new metric, right? It has better regularity than the initial metric. So that's the key point. And if you have only Ricci bound below, right? Then under the condition, right? Rambler point. Original Parman's result is a scalar curvature lower bound and have a local isoparametric inequality. But that's if you have Ricci bound Rambler point, that's imply Parman's criteria. Then you can have a definite time flow and curvature and when you flow a definite time, the second curvature bound by definite number. So that's the key. So, but Parman's the pseudo-locality code is for non-collapsing manifold. But what about collapsing, right? So it's 10 years ago, I asked the question, if there is some strong pseudo-locality hold, right? Means under Ricci curvature condition, every point is local rebounding Rambler point. Can we have this definite time flow and the same thing, right? Same estimate. If you have a affirmative answer to the problem, then the singular nilpotent fibration at least is solved by this under this condition. We have two conditions: Ricci bound below, local rebounding Rambler point; section current below, local rebounding volume point. But at least half can be. It's been a time, and now it's solved. It's solved. Let me explain this. So if section curvature both sides bound, let's say it's open manifold, then you assume the soup is not infinity. then she he proved the existence. Later, Chen Binlong, a speaker, previous speaker, and Xi Pingzhu, they proved the uniqueness. And what about the local wrapper point? Then there is Huang and Wang Bing. They proved there is a local Ricci flow which has the desired property. So local Ricci flow is you have a ball here, you conformly extend the metric on the ball to a complete metric. It's non-collapse. I mean, on the universal cover, local universal cover, non-collapse, then you can flow. So they have this. I think a remarkable result is by Manchun Li. He proved that under this condition, actually it's weaker than this condition, but it implies this result. He gave some estimate, then he showed that under this condition, Ricci bound below local rumble point, the uniqueness. And using this estimate, mentioned Li's estimate, and his result, and combined with Wang's result, one solved the pseudo-locality. Strong pseudo-locality means under this condition, Ricci flow definitely time, and the same curvature estimate holds. Then the similarly important question solved half. There another half is for second curvature bound below. So we want to say that second curvature bound below only the local rewinding volume condition smoothing method failed to apply because it requires Ramberg condition. And here we don't have this because section curvature condition is stronger than Ricci. So the volume condition is weaker. And now I will report some ongoing work. And the result is a generalization of almost flat manifold in the setting Alexander space, a nilpotent fibration theorem, a local boundary common geometry. All has a local boundary common geometry. Yes, all condition has, and some similar applications, and yeah. So let me just report this. Maybe I should. Any questions? Yeah. Before I go in. Main result is if you consider, so I do not give Alexander space. It's a length metric space where you take 3 points, you draw a triangle, then you draw the same triangle. If the Alexander space curvature usually bounded below, right, at some constant, you draw a constant section curvature, 2 space form. Then you draw the triangle. Then the triangle you draw on the manifold look thinner. Then you draw on this. But that's give a control on decent angles. Then their comparison geometry extend to Alexander space. Yeah. For now, I consider the same setting, right? Curvature bound below in the comparison sense. Diameter small, here diameter small has to rely on the volume. The volume of the universal cover, P tilde is the universal cover, universal not collapse. Because you consider unit ball, right? So the diameter, right? So universal is not collapse. Then you have a homeomorphic to a infernal manifold in the same setting, just homeomorphic setting, the conclusion. So that's one result because the collapsing theory start with the Gromov almost flat manifold. You want to do this, you have to start with this. And now you can consider special case, section curvature non-negative, and then you can have, right, you can prove that first Betti number of the Alexander space cannot exceed the dimension, which Alexander space, the dimension is integer, and equal is isometric to flat torus. We know this is the consequence Buckner theorem, right? If you have Ricci non-negative Betti number at most n, right? If equal to n, it's a flat torus. And what about quantitative, right? So you don't assume the curvature is non-negative, but you assume almost, I mean, it's negative, it's lower bound, but diameter small. By rescaling, you can diameter equal to 1, the curvature almost 0, lower bound, almost non-negative. But you can have this homomorphic stability. This is stability quantity. Yeah, so there are early result. I mean, in this Ricci singular space for Ricci, but yeah. And now consider important. Once you have flat manifold, then you have almost almost flat manifold result. Then you consider the same setting, right? Now here you have to assume the sequence has no boundary. It's not just the Alexander space. If the limit is somehow like a manifold, yeah, weaker than manifold, then previously Yamaguchi proved that, right, there is a fiber bundle. However, the fiber only admits metric, I mean, in the comparison sense, almost non-negative, but there are no topological identification. Now, once you have local rewinding volume condition, you can prove that you have a singular, you have nilpotent fibration in this case. The fiber is homomorphic to apply the result. And oh, so now in special case, right, you on the same setting you have fibration. In what time, on what conditions, the fiber is not nilpotent, but it's a flat torus, right? It's a topological torus. If satisfy this condition, the first Betti number of the sequence minor first Betti number at the limit, if it's different, is less than or equal to a dimension unequal, then the fiber has to be a torus. So this is a generalization of Huang and Bing Wang result. They prove in the Ricci curvature setting. So in this proof, right? So you always want to use the condition the universal not collapse. So you have to show this where that's a key ingredient. Otherwise, more or less follow the a similar approach. So the key point you have to show universal not collapse. Okay, yeah, the Ricci setting is this. Next, I just mentioned that in Alexander case, actually, the maximum volume entropy identity of Wang and Redropy, Xiaodong Wang, Redropy can be extended in Alexander setting. I just mentioned, yeah, same setting. Yeah, the volume entropy defined by the local universal, the limit, right? The volume ratio, non-volume ratio, the radius and the volume as R go to infinity, it's upper bound by the volume comparison, cannot exceed n-1. An example is torus n-1 torus cross R1. Universal is Euclidean, yeah. Okay, it's then this has been extended the quantitative version by Chen, Lina Chen. Yeah, I just mentioned this. This spelling not correct. I'm sorry. Okay, And then we consider so-called stability, right? Under what conditions the limit is manifold and the section curvature bound, lower bound. Previously, we see if the both side bound, you know that if it's AS type, spherical manifold, but here we can only prove for the special class if the sequence is a sequence of new manifold, means simply connecting nilpotent. Then the limit, even it's a lower dimension, still a new manifold at the same time. So topological type stability result. And this, I mentioned this early result by the three authors. It's solved conjecture by Petruni, Damaro. It's and the same setting, but if M is a torus, then the limit is a torus. So our result, if you say a new manifold torus, implies there. Moreover, their proof relied on a result where only hold for torus. Basically means if a torus were collapsed, you can rewind geodesic loop, generate, fundamental group. Then on the final covering, the torus not collapsed and diameter is bound. Then apply the permanent stability and some work, you can prove this. But in nilpotent, you cannot expect such that. Any finite normal, there are no, no such a property. So require a different proof, different approach. And here, both work rely on Gromow's result. If you have spherical manifold, Ricci bound below, diameter bound above, universal is not collapse. Universal is not collapse. Okay. So so here, just say what I want to do, right? I think that time is almost up. If you have section curve bound below, now I normalize section curvature, but diameter is 1. Then, right, so this is not result. It's just say, expect to prove that there are singular vibration, the conjecture holds in this case. And local revenue volume, I want to say that hold, that solve the conjecture, singular nilpotent conjecture, the other half, but still in work in progress. And once this result was being established, you hope get you can solve some conjecture in Riemannian geometry for quite a while. So let me stop here and happy 80th birthday, Leo.
Thank you very much. Are there any questions? So I think your situations, you want to kind of study the case where the fiber is a near manifold. Are there, and in a lower sectional curvature bound case, some more cases that the fiber is a kind of manifold with positive curvature. Are there any kind of nice conditions to include that kind of cases?
I haven't, got into that. It could be, you can imagine some non-negative curve manifold, 1 times another 1 times another 1 times another 1, where the scaling are different, but they all collapse to a point. Yeah, so that's a simple model. I don't know. Without this condition, right? They are all simply connected. Yeah. So
okay,
it could be very difficult, yes.
And this counterexample is a rich case, right? So lower sectional curvature case still kind of you may have something.
That's right. That's a hope. That's a hope. Yeah, your volume no collapsing.
Yeah, some people just conjecture that the limit space has stratifications, and you still have some stratified fiber bundle kind of.
That's the long time ago. Yes.
I see.
Yeah.
Okay. Any more questions? Okay. So this is the last talk. So I want to thank Professor Yao and all the organizers and staffs to preparing this wonderful conference. Okay, so the talk is over. Thank you for this.
For this conference, and I think the subject is going strong, and I'm very happy to say that, and I hope all of you will come back. You're welcome anytime to come here. Thank you.